Hello! In this section, we're going to learn about security and authentication. We're going to learn about social sign-on, how to secure our node servers. And we're going to actually implement login using Google's OAuth. Using social sign-on, just like some of the biggest sites in the world. Throughout all this, following security best practices. Now, we could talk about how to implement our own authentication using cookies and tokens, along with some library like bcrypt, just like many other courses do. And that's an okay approach. But in the real world, you'll pretty much never be doing this. Especially on large projects where security is really important, you'll never be implementing authentication from scratch. In fact, you absolutely shouldn't be doing this because you're opening yourself to security flaws, like many that have happened in recent history. Some of these were really clever attacks that are hard to block, but many of them were completely avoidable by using well-proven approaches like OAuth. And there's more and more of these breaches every year. When you re-implement something that's already been done securely, you're opening yourself up to introducing bugs to an already proven system. In the real world, almost always, you'll be using a sign-on service. There's many out there, something like Okta or Auth0 or Amazon's Cognito. Or you'll be doing social sign-on directly, just like we do in this course. The one thing that all of these approaches have in common is that they follow a standard, like what we're going to be learning, which is OAuth, the most widely used way of doing login on the internet. My goal in this section is to teach you real-world techniques and not just toy authentication that is good for learning, but not really applicable to the real world. We've already talked about security a bit throughout the course. We've talked about browser features that prevent you from unintentionally sending data to the wrong servers. That was cross-origin resource sharing, or CORS. We've talked about whitelisting and the principle of least privilege, making sure that we restrict access to only those who need it. And we've talked about auditing our npm packages with the npm audit command to catch any known security issues with our npm packages. But security and authentication are huge topics. Now, let's spend some time to really dive in and explore these fascinating topics in the context of node servers. I'll see you in the section. All right. Before we add any security or authentication, one of the things that we'll be doing most often with our node servers is making sure that they use HTTPS. That's the secure version of the HTTP protocol, which encrypts our data. That is, HTTPS encrypts our data in transit as it's being sent over the internet. So far, our servers have only ever handled requests with the HTTP protocol. But if you remember way back to when we started discussing servers, we mentioned that it's always best to talk to our server and make requests, for example, to some dynamic web page to get some data using the HTTPS protocol, which will make sure that our data for our request is encrypted while it's being sent over the internet to the server, which keeps our client application secure. Using HTTPS, both the requests we send as well as the responses we get back from the server are sent in a way that's private to our user, so that if someone tries to come in and steal our data, well, they can try however hard they might, but they won't be able to crack that encryption and read the data that we're sending, or worse off, modify it somehow. In other words, HTTPS prevents other users from eavesdropping on our data and also from tampering with it. That's what we want. Let's look at exactly how this happens using the SSL or TLS protocols. When we browse to a site using an unencrypted HTTP connection, the data in our request to the server and the data in the response can be read by anyone with access to our network. If we're connected on a Wi-Fi connection, for example, anyone else connected to that Wi-Fi network can read the traffic between us and this server using something like what's called a packet analysis tool, something like Wireshark, which can potentially inspect all of the traffic that's crossing our network. Wireshark is a little bit beyond the scope of this course, so if you're interested, check out an ethical hacking course. But what we need to know is that Wireshark has this ability to inspect traffic as it's being sent across our network. And it's especially easy if it's not encrypted. That's not great if the traffic that we're sending, say in our request, includes a password or some other data we'd rather keep private. On the other hand, when we browse to a site like Google using an encrypted HTTPS connection, which we can see in our address bar, what happens is that we're now using the encrypted HTTPS protocol that underneath the hood uses the powerful encryption of SSL and TLS. SSL and TLS are usually used to refer to the same thing. To be fully accurate, TLS is actually the successor to SSL. TLS is the latest version of this encrypted protocol. So we started off with SSL 1, 2, and 3, and then moved on to TLS 1 and kept getting new versions from there. But many people still say SSL when referring to TLS, so it's good to be aware of both terms. HTTPS doesn't change the HTTP protocol. We still have that same old HTTP connection, but we now take our HTTP requests and responses and wrap them in this really strongly encrypted connection provided by TLS. And it's this strong outer shell that becomes our HTTPS connection. Only the domain name of the site you're browsing to is exposed in what's called plain text, because the domain is needed to set up that connection. But all of the data in the body of the request and any specific paths that you're browsing to are all securely encrypted with TLS. Say you're browsing Google and running some searches. Anyone snooping on your connection will know that you're browsing google.com, but not what you're searching or what data you're sending and receiving. That's kept secure because Google uses TLS and the HTTPS protocol. Let's dig just a little deeper into TLS in the next video. We'll find out just how it keeps HTTP secure. I'll see you then. Welcome back. We've learned that HTTPS uses the SSL and TLS protocols to encrypt our HTTP connections. Now, for our data to be encrypted, we need what's called a SSL or TLS certificate. This is a type of digital certificate that's used to verify the server's ownership prior to any encrypted data being sent. Just like on a physical certificate that you might sign, if the digital signature of this digital certificate is valid, and we trust the person who issued this TLS certificate, then we say, okay, I'm willing to use the key that this server sent to send encrypted data back and forth with that server. This is used to verify that we're actually talking to the server that we expect. It's not enough that the data is encrypted if we're sending encrypted data to some malicious hacker who has the key to decrypt that data. That's what's called a man-in-the-middle attack, where a hacker pretends to be the server that we're talking to and instead steals that data for their own purposes. With digital certificates, we verify that server's ownership first to prevent these man-in-the-middle attacks. Now, we mentioned that these certificates are signed, and they're signed by what's known as a certificate authority. This is an organization that your computer or your browser already trusts to issue valid digital certificates that actually verify the real server's owner and aren't just created by some malicious hacker. Now, in the early days of the internet, you had to buy these certificates from certificate authorities that would potentially cost hundreds of dollars. But lucky for us, there's now certificate authorities that allow us to sign these certificates for free. One of the most well-known is Let's Encrypt. They're backed by Google, Facebook, and all kinds of other giant companies to provide you with the same security without the added cost. However, Let's Encrypt will only give you a certificate if you meet certain conditions. For example, your site needs to have a domain name and can't just be an IP address on some server somewhere. This is why we have a type of certificate called a self-signed certificate that still allows us to encrypt our traffic and use HTTPS, but we sign it ourselves on our local machine. And our local machine, our certificate, isn't trusted by others. We're not registered as a certificate authority, and we haven't built up that reputation that these large CAs or certificate authorities have built up for themselves. Companies like Google and Facebook. So self-signed certs are useful for development because we can sign them for IP addresses like localhost, but they're not useful in production because they're still vulnerable to those man-in-the-middle attacks. There's no trusted third party, no certificate authority to verify who you're talking to. Because of this flaw, if your browser detects a self-signed certificate, it will give you a warning much like this one, telling you that the certificate authority is invalid, and you'll only be able to browse to the site if you explicitly tell your browser that you understand this risk. This is why in production, we always want to use CA, or Certificate Authority signed certificates. Because they're signed by these certificate authorities, they're trusted by most clients on the web, and your browser will tell you that the server you're talking to is trusted. Only the server registered with the certificate authority will pass that check. All TLS certificates can be broken down into these two categories. Just like the TLS protocol encrypts your traffic, additionally, these certificates help to verify the ownership of the server you're talking to. And that's really what you need to know about TLS. Let's keep exploring in the next video. I'll see you then. How do we get our node servers to use HTTPS? How do we get them to respond to HTTPS requests and to use this powerful encryption in our APIs? Say we have this bare bones Express server. Nothing new here. This will be review, so if you're really impatient, feel free to skip this video. And the code we write will be available as a resource attached. Let's take a look. We have an npm package in this security-example folder with Express installed. And our server.js has an Express application that's listening on port 3000 using the listen function on our app object. And we have just one route, this get, that is serving this index.html file in the public folder that's in our current directory. And we're using that path.join function from the built-in path module to make sure that the path to index.html is valid on any operating system. That's pretty familiar, so let's take a look at index.html. Again, this is a bare bones HTML file where we just have a title saying that this is our security example, and we're just writing hello in bold. I'll include this code attached to the video. But basically, writing out all of this HTML and talking through it would be pretty boring. So let's get to the interesting stuff. What we're going to do is encrypt all of the data coming in and out of the server by using SSL certificates and the power of HTTPS. So for our demo, I'll add just one endpoint where we can get some secret data. So let's say it's app.get on this /secret endpoint, and it'll take in our request and response. For now, just return res.send your personal secret value is 42. All right, as it stands, this value likely won't be very secret. But we're responsible, so let's see that our program works and do npm start. All right, the server is listening on port 3000, which means if we go to our browser at localhost on port 3000, we're getting that root route, which is serving our index.html, telling us hello. And if we go to our secret route, we can do that as well. Check it out. But as you already know, this data and our secret value is being sent over HTTP by default, which means that the connection to our API is not secure. Anyone on our network listening to our traffic will see that the response to our request here included our secret value of 42. Let's fix this. Let's make it a lot harder for any nosy hackers or even other software that's listening to our traffic to know the data that we're sending back and forth. Now that our HTTP server is set up, we can secure the communication between our browser and the server so that when the secret here is sent, it's being sent encrypted. For that, I'll see you in the next video. It's going to be a good one. Here we go. Let's put HTTPS to use in Node. There are many ways of using HTTPS with Node servers. Many services exist, for example, on Google Cloud or Amazon's AWS. These services, like Amazon's CloudFront, allow any server to automatically be served over a content delivery network. So your pages get served from the closest locations in the fastest way possible. That's a neat feature, but what we care about is that included in these services is the ability to automatically serve your content using HTTPS. However, I want us to add HTTPS to our server in Node, in our server code, just to have the knowledge of how it works, but also to understand how to test that our servers work correctly when using the secure HTTPS protocol, because this is something that comes up fairly often in our Node projects when we're building sites that pass private customer information, like credit card numbers or personal health information. We want to make sure that our servers respond to HTTPS requests correctly, even when we're running on localhost. Remember how there were two ways of starting our HTTP servers? We could use the listen function from Express's app object here, or we could require our HTTP module. So const HTTP equals require HTTP, and then call the same listen function, but this time from Node's built-in HTTP module. So http.createServer, which is a function that returns our server, which has this listen function. The reason why we sometimes use this longer way of creating our servers is because of the additional flexibility it provides. For example, just like we have this HTTP module, we also have HTTPS in the built-in HTTPS module. If we now call https.createServer, the really cool thing we can now do is pass in an option into createServer, this object, with our SSL certificate, which then encrypts all of the data being sent to and from our server. So what we do is we pass in this cert option, which is a string containing a path to that certificate, as well as this key, which contains a secret used when we encrypt our data. We're going to use something called OpenSSL to create that certificate. This is an open source tool that's available both on Windows, Linux, and Mac systems. On Windows machines, if you don't already have it installed, the easiest way to get OpenSSL set up on your machine is by installing Git for Windows. If you have Git for Windows, you should already have OpenSSL set up. And on macOS and Linux, it's quite likely you already have OpenSSL installed as well, or you can get it from the openssl.org page right here. When we have OpenSSL on our machines, we can go into our terminal and generate a self-signed certificate by running the OpenSSL command and pass in REQ to request a new certificate. We use the -X509 option to tell us that it's a self-signed certificate, with a dash new key that contains that secret used in our encryption. This is also known as the private key, which uses the RSA encryption format, where RSA is one of the strongest forms of encryption which much of today's technology relies on. With RSA, we can specify the size of the key. That is, the amount of bits which the data in that key takes up. Generally, a larger key size means that our encryption is stronger. So we want really strong encryption here, which means we'll say 4096 bits is how large our key will be. This is a common value. We can specify the -NoDES option, which allows us to access this new private key without needing to assign a password to access it. Since we're just using this new self-signed certificate for development, a password is not necessary, and it'll just add more typing work for us. So that's why we pass in -NoDES. And with those options set up, we can now say that the key should live in a file. So -keyout, the output of our key, will go into key.pem. PEM is a common format you'll see used for certificates, both for the private key as well as the actual certificate, which we create with just the -out flag. And we specify the name of our certificate file, which can be something like cert.pem. So now the result of this command will be two files, the private key and the certificate. This certificate, which is public and which our browser will check to check the ownership of our server. And last but not least, we specify how long the certificate is valid for. So in days, we'll say that for our purposes, 365 days is how long this self-signed cert will be valid for. After that, we need to generate a fresh one. If we don't specify the number of days here, it's usually only 30 days. We want it to be long enough that we're not always generating new certs, but also not forever in case the certificate is stolen or something about our application changes. The certificate is a bit like a driver's license or a passport photo, which you need to update to confirm your identity. All right, I know this is a long command. Don't worry, normally you don't have to memorize all of these options. It's just a Google search away. And creating certificates is usually something you do just once per project, or maybe once per year. And you can always use this video as a reference. Let's make that cert. We're asked for some options, a country name, which we can leave blank, or we can write our two-letter country code. We can leave the state or province empty, as well as the next few options. The important one being the common name, which usually when your certificate authority is signing a certificate, they'll set the common name to be the domain name, like www.google.com. That has to match the site that your browser is currently looking at. But for self-signed certificates, we don't necessarily have a domain name. Maybe we're just running on localhost or an IP address, so we can just write our own name. I'll write Adam, and we can leave email address blank. Now what we have, if I close the terminal, we have two files, cert.pem and key.pem. Check it out. This key contains what appears to be 4096 bits that ensure that we're the only ones encrypting data for this server. So ownership of the key means that we're allowed to encrypt data for the server identified by the cert. And vice versa, the certificate actually allows you to decrypt data encrypted with this key. So that's what the browser would do. It decrypts the data sent from the server, encrypted with the private key, using the data contained in that certificate, which is why the browser requires access to this public certificate. This approach that I'm describing is what's known as public key cryptography. That's what SSL and TLS use to make sure that your data is kept safe. With these two files available, we can now set the paths when we create our server. So the key is going to be in key.pem, and the cert is going to be in cert.pem. Let's run that server. I'll clear our terminal and do npm start. Oops, and if you see a error like pem no start line, it's possible you've made the same mistake I have. When we create the server, we need to actually use the built-in file system module. So I'll import that, const fs equals require fs, and I'll just rearrange these imports. I like to have them following this line of longest to shortest with the built-in modules at the top. I know some people like to keep them alphabetical. That's fine as well. So what we do with the fs module is we call fs.readFileSync and pass in the paths to our key and certificate to load those files first before passing them in as options to our createServer function. So let's do that for the certificate as well. fs.readFileSync, reading the certificate synchronously before starting up our server. Both of these files are required before our server can start listening. Oh, and before we start this, we also need to make sure that we're passing in both arguments to our createServer function. So our first argument is going to be this options object with our certificate, and the second is going to be our request listener. That's our express application. Now our server should respond correctly. So let's give this a go. One more time. npm start. Looking good. Which means in our browser, if we refresh the page, we get no response from the server. This is because there's no HTTP server on localhost at port 3000. Well, there is, but it's only serving traffic that's using HTTPS. And so we need to add that to our URL. Let's see what happens. Most likely, we'll get some kind of notification from our browser telling us that there's a problem with our connection to the server. And our connection is not private. Why? Because the certificate authority for that self-signed cert is invalid. Adam is not a trusted certificate authority that our browser recognizes. For self-signed certs, every browser will be a little bit different, but we basically have to confirm that we're aware we're only testing our HTTP server using this self-signed certificate, and that we trust this particular server. So on Chrome, I'll go to the advanced settings, and again, Chrome tells us that the server could not prove that it is localhost, it couldn't prove its identity, and that the security certificate is not trusted by the operating system. So if we're aware of that risk, we can continue to proceed to localhost. And once we do this, the browser should remember that we trust this particular certificate. There we go. We still get this not secure warning because our certificate is invalid, but our site is now using HTTPS. And if we go to the developer tools of our browser, in our network tab, we can refresh the page and we'll still see the request and response. But anyone snooping on our traffic from another machine, for example, would only see the encrypted bits and bytes being sent back and forth. Remember, certificate authorities like Let's Encrypt normally give us signed certificates for production sites with their own domains, like www.google.com or mysite.com. When we run our server on localhost, we'll need to create a self-signed certificate when we're testing our server, and configure Node when we set up our HTTPS server to use that self-signed certificate. We are now done. And in the process, we've learned a lot about how certificates work and become better developers. Let's keep going in the next video. I'll see you really soon. Bye for now. Let's talk about Helmet. When our server is ready and handling HTTPS requests, what's the next most important and common task that we do as Node developers? Well, we need to secure our server against common issues. Issues with how our server is configured, issues with how it handles incoming requests, and with the data that we send back. For example, we don't want our response to leak data that's going to be exploited by hackers trying to break into our server. We'll explore these issues in just a second. But first, what's this Helmet thing? Helmet is a widely used NPM package that contains a collection of middleware. Middleware that helps us secure our server, plugging all of the most common holes that Node servers might have. So scrolling down here on the Helmet website, when we add the Helmet middleware to our application, what we're really doing is adding all of these middlewares that each protect against one type of security issue. For example, we have hide powered by, we have HSTS, and we have a content security policy. These are potential problems or added security features that apply to pretty much every application. Although we can choose to enable and disable these middlewares individually if we so choose. But again, because these are problems that everyone experiences, we have these reusable express middleware that help us make our server more secure. Each of them is available as an individual package on NPM, but grouping them together makes it easier for us as developers to cover all the possible scenarios. Let's add Helmet to our security example. By doing so, we'll explore exactly what it does for us. We'll start in our terminal by npm installing Helmet. With that complete, we can now require the Helmet middleware. So const helmet equals require Helmet. And just like any middleware, we want to call app.use, calling that Helmet function, which returns all of that middleware grouped together. But where do we add the Helmet middleware? This is important. Generally, for security-related middleware, we want to add it right at the top of our middleware chain. For example, we would call app.use with the Helmet function right at the top before any of our routes so that every request passes through the Helmet middleware, regardless of where we respond to it. Let's do a little comparison. First, I'll comment out the Helmet middleware and run our server just like we did before, npm start. And let's take a little closer look at the responses we get back from Express. In our browser, let's open the Developer Tools and take a look in the Network tab what happens when we refresh our secret endpoint. We get our response as expected, but there's some extra data here that we might not have noticed. In the headers, we have some of the things we expect, like the status code being 200, and scrolling down in the response headers, we have the content type being set. But look down here, we have this x-powered by that's set to Express. This tells anyone making a request to our server that it was built with the Express framework. This is a way of giving credit to the Express developers. But it also potentially gives someone trying to poke holes at our server a little bit of extra information for free. If there were some widely publicized issue with Express that allows an attacker to leak all of the data in our server or run arbitrary malicious code, well, that attacker would have all the information they need to target our server just by searching for this header. When it comes to security, it's often a good idea to be minimal, to send the minimal set of data that the user needs, to give users the minimal permissions to do what they need to do. So now if we go back to our code and enable the Helmet middleware, let's restart that server. And if we make this request again, let's inspect that second request. We're still getting our content type, but if we scroll down, we're getting all these extra headers now, but check it out. No X powered by. We're not leaking that information for free. But these extra headers that we've added all have very important purposes that help keep our API secure. For example, we have this strict transport security header, which refers to that HSTS feature we saw on the Helmet website. HSTS stands for HTTP Strict Transport Security. This header tells the browser that it should never talk to your API using HTTP, and all HTTP requests should be automatically converted to HTTPS requests instead. It's common for developers to build their web servers to accept both HTTP and HTTPS requests and point the users to the secure version by redirecting them if they visit the HTTP version first. The first time that your site is accessed using HTTPS, the browser will remember this header and make sure that all future requests use the encrypted connection. And that's just one of the headers that Helmet adds. We have XXSS protection, permitted cross-domain policies, frame options, DNS prefetch control. All of these X- headers that were added by Helmet. And scrolling up, we also saw this content security policy, which controls which resources the browser is allowed to load for your current page. This is used to protect against what's called a cross-site scripting attack, where a malicious user, rather than saving some data to your database, instead saves a script, which is then run by all of the users using your application inside of their browser. With cross-site scripting or XSS attacks, these hackers run their malicious scripts with all of the permissions that your application would normally have, which means they can steal things like your users' cookies and session tokens, which are things that we're going to talk about in this section. It sets all of these headers that affect the security of your application. You can go ahead and read up on all of these different headers, and I'll attach some resources as well. Going through them will give you a review of the current security features in browsers and overall security best practices. Helmet is staying up to date with browser features and adds new middleware as these new security features are introduced. It's a really good package, and I install it on pretty much every server I put in production. As the Helmet developers themselves say, it's not a silver bullet. It doesn't solve all of your problems magically, but it can help. And with that, I'll see you in the next one. All right, welcome back. In many of the sites that we build, we want to add the ability for our users to log in. We generally want users to log in if we need some parts of our application to be protected so that not all users can view everything in our application. For example, if our server stored some data for 3 users, Andre, Larry, and Dwight, chances are those users might want to protect that data. In case these are secrets on some website, we want to make sure that the user accessing the data is trusted and allowed to access that particular resource. When it comes to login and securing the data in our applications, there's 2 main concepts that are often confused. I know I get them confused all the time. There's authentication and authorization. Authentication validates that users are who they claim to be, usually with a username and password. Whereas authorization checks whether that user has permission to access a specific resource once they've been authenticated. Let's really understand the difference. First, what we've seen so far is when we have neither authentication nor authorization. In these cases, our users can access our website without proving who they are. They're anonymous users. And once they get access to our site, they can access all of the data that's contained within. So if our user here was Dwight, well, our site doesn't know that, so Dwight can access Larry's text file with Larry's secrets. If we wanted to secure this application, here's what we would do. We're now using authorization and authentication, so our secret site is now secure. When our anonymous user tries to access our site, we have our first check, this stop sign where the user needs to log in to prove they are who they say they are. This is the authentication step, where our user is now proving that, in this case, they're Andre. Usually this involves registering for our site and logging in with a username and password. But sometimes it can involve biometrics. For example, using a fingerprint on your phone. That's still authentication. Or in some cases, we might have what's called two-factor authentication, where a user needs to prove they are who they say they are, not just with a password, but also with a security code that's either sent to them by text message or, more ideally, available to them in some other more secure way, like through an authenticator app on their phone or some dedicated device, what's called a hardware authentication device. These are more secure because text messages can be faked and potentially read or intercepted by attackers trying to get access to your account. Authentication is proving with as much certainty as possible that the user using your site is in fact who they claim they are. With Andre authenticated, he can now access secrets.com and make authenticated requests against the different data and endpoints in that site. But now Andre tries to access Larry's data. And we have this second checkpoint, this second stop sign, which checks whether Andre is authorized to access this particular resource, whether he has the privileges required. In this case, because these are Larry's secrets, this check fails. Andre can't access this data. But now, if Andre tried to access his own data, well, that check passes. Andre is authorized to access his own data. Authorization is sometimes called access control because it controls which resources in the server the current user has access to. It checks what you have permission to do, whereas authentication is just the key to this door, which only gives you access to a user with the correct credentials. These two concepts of authorization and authentication are sometimes combined into what we call auth, which is convenient because both terms begin with auth, authorization and authentication. But this is often the cause of a lot of confusion about the difference between both terms. Hopefully that'll be more clear to you now. Oh, and by the way, this knowledge applies to our HTTP response codes as well. Remember, under client errors, those 400 series status codes, we had 401 unauthorized and 403 forbidden. The naming for these was quite poor. As you can see, the 401 unauthorized isn't correctly named. In reality, it means unauthenticated. If you haven't logged in and the site has been secured, chances are you'll get the 401 unauthorized status code. Whereas if you are logged in or authenticated, but you don't have the right permissions to access the resource, chances are you'll get 403 forbidden. We have authentication and authorization. Authentication is the login and authorization is the permissions. All right, on that note, I'll see you in the next video. What is social sign-on or social login? Right now, I'm on medium.com, which is a publishing site that lets you post articles and blog posts. I'm going to use this as an example, but social sign-on can be applied to pretty much every site if the developers of that site choose to include it as a feature. To log in to my Medium account, I'll go to this sign-in page, and I'm presented with this option to sign in with many different social providers, with these sites that I might already have an account on. For example, Google or Facebook. There's many different possible providers, even beyond what you see here. For example, GitHub is also a common option for more developer-centered websites that know that their users are likely to have GitHub accounts. Right now, I don't have a Medium account, but I can create one by going to this option to create an account and use my Google credentials. I'll sign up with Google, and because I'm not logged in with my Google account yet, I'll do that first. Click Next, and type in my password. When I complete this step, I'll now have a Medium account, just like that. But no need to remember a specific set of credentials, a username or password, specifically for Medium. As long as my Google account is secure and I'm logged in, I can access Medium with that account. You can see certain information from my Google account has even pre-populated certain fields in my Medium account. So I didn't ever need to put in my name. Medium just grabbed that from my social account. If I go to google.com in a different window, you can see that I've now signed in with my Node developer account. Because I'm signed in, the next time I go to Medium, I don't need to put in any credentials. Even if I log out from my Medium account, because my Google account is already logged in, I can do sign in and sign in with Google and check it out. I can now read all of the blog posts that are recommended to me on Medium for my fresh account. Chances are, if this is my machine, I'll already be logged in to my Google account, which means signing into sites like Medium will be a matter of pretty much just 1 or 2 clicks. And I have one less password to remember. That's what social sign-on is all about. Now, from a development perspective, Medium is still keeping track of who's signed up. It still knows that Node developer is one of Medium's users and that Node developer signed up with Google. But it's much more convenient for Medium's users to have this option. And it saves Medium from having to implement functionality to create new accounts, reset passwords, and to keep those passwords secure, which is no easy task. When we add social sign-on to our applications, to our sites, what we're saying is that, 1, we want things to be more convenient for our users, but also 2, that we trust Google to keep our users' passwords and accounts more secure than we would ourselves. And it doesn't matter what kind of world-renowned security expert you ask, they'll agree that a giant company like Google or Facebook is more likely to keep your passwords secure and stay on top of security issues than a small team of developers doing it themselves from scratch. You take advantage of all the work that Google's developers have already done and the millions of dollars that Google has invested in security. It's great stuff. All right, let's keep exploring in the next video. I'll see you soon. Welcome back. There are 3 main tools that developers use to make sure that only authorized users can access a server and its API. Sometimes we restrict access to our API with what's known as an API key. Sometimes we use OAuth tokens, and sometimes we use what's called JSON Web Tokens, or JWT. Let's start by discussing API keys. An API key is a string value that we use for 2 purposes. The first is as a unique identifier for your project. for your application so that the server you're making a request to from your application knows which application that request came from. And the second purpose of API keys is to grant and restrict access to some API. API keys are usually used when the users of your API are developers trying to enable some functionality in their application that makes use of the features that you've already exposed in your API. Sometimes these API keys are public. That is, anyone can view the API key for some application. For example, if I go to the Starbucks store locator here, and I'm looking up all of the stores in Vancouver, Canada, I can go to the source code for this page, and if I search key equals, I get a result with this Boomer API key, and check it out, I have the value right there. API keys are often public when they're just used only to identify which app is using this API. For example, in this case, this Boomer API is being used for real user monitoring. It's tracking the users of this Starbucks application and is mostly being used to identify that requests to this Boomerang API are coming from the Starbucks app or the Starbucks website. But usually, you want to keep API keys private by making sure that they're available only in the server, on the server side, and not in your front-end JavaScript like we see with the Starbucks site. We normally use these API keys when an API is designed to be public or easily accessible, but the owners of that API, of that server, still want to make sure that the API won't be abused. Normally, we associate each API request with an API key by passing in that API key as either a query parameter or as a header in that HTTP request. Now, with each API request being associated with some API key, if, for example, too many requests come in too quickly from one API key, what can the server do? Well, if that server wants to limit the amount of requests that are allowed per API key per minute, that API, that server, might send a 429 too many requests response, which indicates that the user has sent too many requests in some given amount of time. This is what's called rate limiting. And it's a great idea when you have an API that's exposed to the public. You want to make sure that your API is accessible to everyone and that a few users aren't overloading your API with millions of requests per hour, which can cause your server to become unavailable to all those other users. Or in some other cases, the owners of an API might suggest that you upgrade to a higher tier that might cost more if you want to make more API requests per minute. API keys are great at enabling these kinds of checks when you expose your API to the public. One example of a platform that uses API keys is Google Maps and the Google Maps API. Say you wanted to display a map on your website with all the different locations of your coffee shop. You'd request Google Maps to display that map of coffee shops with some API key attached. when you load the JavaScript to show the map, you would include the API key as a query parameter in your request to load that JavaScript. This is a tool that Google uses to make sure you're not overloading their API with too many requests. How do we get one of these Google keys? Well, we can go to the Google Cloud platform with our Google account, and we might need to create a project. So I've created Cali Coffee Shop Chain, and then we might need to enable the Google Maps API in this library page. So I'll enable the Google Maps JavaScript API for our website and enable that, which now means under Credentials, I can go here under API keys and make an API key for my Cali Coffee Shop. I might have to go to this more general Credentials in APIs and Services page. So I'll click on that link first. And here I can create different types of credentials for my Google project. So I'll create credentials, and I'll select an API key, which Google summarizes very well. It identifies your project using a simple API key to check quota, that's the amount of requests per minute, and the total number of requests, and access, making sure that your application has the correct privileges. So let's go ahead and make an API key, which we see looks like a series of fairly random letters and numbers. We even have an underscore in there. And normally we would copy this API key to use in our application. But first, what we want to do is restrict the key so that it's used correctly. Let's see what options we have. If we go to Restrict Key, Google provides us with many different ways of restricting how this API key is used. So scrolling down, we can restrict our key to only be used by websites using HTTP, or to certain IP addresses versus certain domains or URLs for the first option. And we can even restrict to certain Android applications or iOS applications. For this key, for our Cali Coffee Shop, we would want to restrict the URL that it could be used for to the production URL for our coffee shop website. So we could add an item and say www.calicoffeeshop.com. The API checking our key would then only allow requests from this site using that key. In case somebody steals our key and tries to use it for their own site at www.texascoffeeshop.com. We also want to follow that principle of least privilege, giving this API key the minimum amount of permissions that it needs, which in this case is for our store locator to display all of the locations of Cali Coffee Shop chain. So we'll restrict the key, and with the Google Maps API enabled, we should see the Maps JavaScript API in this dropdown here, along with all of the other main Google Cloud APIs that are enabled for our application. And that's how we secure our API keys, whether they're for maps, tracking our users, or any other API service. Overall, API keys are great if you want to just make sure that your API is being used appropriately by some application. But sometimes we want to be more specific in how we give different types of users different credentials, different permissions to use our API. Let's explore some more approaches in the next video. I'll see you soon. Welcome back. JSON Web Tokens. What are those? Apparently, they are an open industry standard RFC 7519 method for representing claims securely between two parties. What does any of that mean? Let's break it down. To start, JSON Web Tokens, also known as JWTs, are a type of access token. Access tokens are much like API keys. They uniquely identify a specific user of an application. But more than that, they act as a set of credentials for that user to grant access to an API. When a user is browsing our site and they authenticate with our server API, so they're logging in with a username and password, if their username and password are correct, the server will in return give the user one of these access tokens, and they then pass that token in every request to the API so that the server can validate that the user is authorized to perform whatever request they're trying to make. For example, trying to get their user data. This flow is what's known as token-based authentication, which is sometimes also known as bearer authentication, because the person carrying or bearing that token is the bearer. They're in possession of this token that can be used to access some specific resources on the server. When we have one of these access tokens or bearer tokens, we pass them in as a header in our request, where the name of the header is authorization, and the value includes this word bearer followed by your access token. The two most common types of tokens are opaque tokens and JWT tokens. JWT tokens follow the JWT standard. That standard tells API developers how to decode these tokens so that we can validate that token before trusting it to respond to some request, and to verify that the correct permissions have been granted to that token. The other type of access token is what's known as an opaque token, where it follows some format that's not understood by the server. To validate this kind of token, our API will usually make a request against another server somewhere. That server which issued the token in the first place, the server that created it. But JWTs are nice because they don't require this additional request, and they can be extended with any additional functionality that your server needs. Let me show you what I mean by extending the functionality. Back on the jwt.io page, if we scroll down, we can see an example of a JWT token. That's it right here. It's just a string, a bit longer than our typical API key, but it looks pretty random. Here's where it gets interesting. Remember, JWTs are credentials, which can grant access to resources. Credentials can include different types of information. Your passport, for example, is a type of credential that you carry around when you want to travel to another country. Your passport includes things like your name, your citizenship, and your photo. But some countries may choose to include additional data. For example, some additional identifying information, and even sometimes biometrics, like fingerprints. Just like a passport can be customized to include different types of data, a JWT can also be customized and extended to include additional data. Right now, the JWT that we see on the left here includes the data that we set as the payload right here. This JSON object with the sub and IAT fields, which we'll get to in just a second, and the name field, which is a custom field. And this is a JSON object. I just need to scroll up on this to show the entire thing. There we go. Because this payload is captured by the JWT token, if I add some piece of information, say a country field that specifies Mark is from the USA, the JWT token is updated with that information. Or I could add a field that says that Mark is an administrator, so setting admin to true. The server can then use this information when it checks the JWT token and determines which resources it grants access to. The JWT token is a piece of encoded information. It can be encoded and decoded to get the plain text, the plain JavaScript object, by using what's called a base64 decoding function. The JWT token is just the data in the JSON object encoded in base64. Every JWT can be broken down into 3 sections: the header, the payload, and the signature. The header is set in this red JSON object over here. We always set the algorithm to some value, which we'll talk about in just a second, and we set the type of the token to be JWT. The algorithm and type of the token are represented by this red part of the encoded token right here, while the payload, here in purple, is included after this dot in the purple text section. And then finally, we have this signature, which uses this HMAC SHA-256 algorithm, which is specified in the header here. HS-256 is short for the HMAC SHA-256 algorithm, in this case, to sign this token. Just like we signed our SSL certificates when using HTTPS, we sign these JWT tokens and include the signature as the last component so that the server can verify that the token was not tampered with. This token can only be encoded with a valid signature by the server, which has the secret used in the signature. But it's important to understand that JWT tokens are encoded and signed with this signature, but not encrypted. Anyone can paste any JWT token into this site here, and you can get the information contained within by decoding it. The signature here only prevents manipulation of existing tokens or the creation of fake credentials, of fake tokens by malicious users who are trying to get access to our data. Where, for example, I replace Mark Rober here with Bill Gates. Only the server with the secret used in the JWT signature will be able to create new valid tokens and change the name in our payload. The token can't be tampered with, but it can be publicly read by anyone who gets access to that token. Because of this, JWTs rely on the secure network communication that HTTPS and TLS give us to make sure that hackers can't steal our token and reuse it for their own requests. Remember, just like your username and password, the token gives access to all of your data in the server. Just like you want to make sure that your password is only sent over an encrypted connection, the same applies for our bearer JWT tokens. Token-based authentication only works when you're using HTTPS. Otherwise, it's not very secure. Before we go, what were those sub and IAT fields in our payload? These are optional fields that are part of the JWT standard. Every piece of information that's captured by our payload is known as a claim, something that the JWT token is claiming to be true. The sub specifically is the subject identifier. It tells you who this token carries information about. This is usually represented by a unique user ID or hash. So each claim in the payload is made about the subject. And IAT is short for issued at. It's the time and date when that JWT token was created. This can be used, for example, to determine how old this token is. And there's other optional claims that you can make in JWTs, like when the token must expire or who issued that token. We can keep adding information about our subject into these tokens and have access to it directly without needing to look up that data in some other database. In theory, this sounds nice, but I find in general it's best to limit the amount of data that we put in our JWT tokens. After all, this is data that's constantly being passed around from the client to the server, and its purpose is to grant access to our subject so that they can use our API. So generally, we should keep the information in our JWTs to the information that identifies the user and their access to the API, as well as any metadata that's needed to validate that token, to make sure, for example, that it hasn't expired. Because tokens are associated with individual users, and they allow us to pass around this additional data, which can be verified on the server side, they give us more flexibility with which permissions to grant individual users than a general application API key might allow. And with token-based authentication, possession by a user of a valid token gives them access to an API for as long as they have that token, rather than having to log in over and over. Let's continue exploring and see one way that JWTs might be used in the next video. I'll see you in a bit. Welcome back. One of the most widely used approaches in implementing login, used by everything from Google to Facebook to GitHub, is what's called OAuth. What's OAuth? It's an authentication standard that enabled things like social sign-on to become so widespread. OAuth, or specifically OAuth 2, defines the flow or process that goes on behind the scenes when you log on to a site like Google. This flow isn't the simplest for developers. We'll go over it, but it's often the point of confusion, and it has quite a few steps. So why do we need this? Why add this complexity when you can just put in a password to access some data? The problem that OAuth tries to solve is that we want to let a user access some application, some web app, without necessarily putting their password into that unknown, untrusted site. Notice if we log in on Medium and choose the Sign in with Google option, we're now on Google's page with Google's domain, with Google's certificates. So we know we can trust this page when we put our password on it. With OAuth, we'll always see this official Google login screen, and we'll only need to put our password in this one place, at what's called the OAuth server, which in our case is Google. You don't put in your password in the application, Medium will never know your password to Google, and instead you're sent to Google's servers, or GitHub, or whatever OAuth server you're logging in with. And following this flow, that authorization server will eventually give you back an access token, which you can then use to access data inside of your application. You never had to put your password in to the web application, to Medium. This helps keep your password safe and minimizes the amount of passwords that you need to keep track on different websites. Google internally uses OAuth as well. Notice when I'm signing into Medium, I'm on accounts.google.com. And when I try to sign in on google.com, I get sent to the same OAuth server. And the same would apply for YouTube or Gmail. It's always this one server that handles authentication. This helps Google ensure that they can secure this one server really, really well, and it minimizes what's called the attack surface, the amount of different servers that can be attacked by hackers. And the added bonus is that Google can keep all of your accounts in one place. I can even, if I log in to Medium with my Google account, let's do a little demonstration. Say I no longer wanted Medium to have access to my account, and I wanted to revoke login using my Google account. I could go to my account settings, somewhere here under security, and revoke access so that I can no longer sign into Medium with that Google account. Notice that Medium is listed under apps with access to my account, and if I go to that option, I can see what Medium has access to, including just some basic personal information with my primary email address, and I can remove access. Next time I want to log into Medium, I'll need to grant access with Google again. This is great if I no longer want to link Medium with my Google account. I can revoke consent, and that app will no longer be trusted. I hope you see there are some benefits to using OAuth when you sign in, especially from the perspective of a user who wants to keep their account secure and minimize the amount of logins that they need to keep track of. That's the reason it's so widely used. All right, let's go over that OAuth flow in the next video. I'll see you soon. Here we go. Let's understand exactly what the OAuth flow is all about. We'll start by looking at the different roles, the different things involved in the OAuth flow. We have the resource owner, we have the client, we have the resource server, and finally, the authorization server. These are 4 important terms that are defined in the OAuth standard. Let's make sense of this. The resource owner is just a fancy term for the user. When you log in to Medium using your Google account, you are the resource owner. And as the user, you're using your browser, you're using a user agent to talk to the client. The client is just the web application that is going to try to access some protected resources, some protected data for you, for that user. And that protected data lives behind some API, maybe in a database, on the resource server. The resource server is often the backend for your application. So if a client is myapp.com, the API for myapp.com is going to want to restrict certain data so that only I can access it. And with OAuth, the way it does this is, you guessed it, using the authorization server. This is the server that authenticates the user or the resource owner when they log in and gives them access tokens so that they can then access the resource server. If we're doing social login, then the authorization server can be something like GitHub or the accounts.google.com server that we've seen is used both internally by Google as well as when you try to sign on with a website like Medium with your Google credentials. This authorization server is possibly the most important piece of the OAuth flow. The truth is, there's not just one OAuth flow. OAuth 2 supports the authorization code flow, as well as the implicit flow, and even the client credentials flow. You have a few different options. However, the authorization code flow is the most common and is the gold standard when it comes to security. We use the authorization code flow when your application has both a front end and a back end where you can securely store secrets. And so for all those reasons, we're going to be looking at this standard authorization code flow, which is what we see here. This is a redirect-based flow, which starts with your web application making a request to some authorize endpoint inside the authorization server, which in our case is going to be Google. So the browser starts by making a GET request against the Google servers. The Google authorization server then redirects you to an authentication prompt where you put in your username and password and consent to allowing this web application to use your account to log in. If you log in successfully, the authorization server sends you back this authorization code, which is where the name for this flow comes from. This is a temporary, short-lived code that our application then sends back to the authorization server along with a client secret that usually lives in your application's server to get back the access token that the user can then use to make requests against the API for your application. This access token is often a standard JSON web token. It doesn't have to be, but oftentimes authorization servers use JWTs for this token. In fact, the idea of bearer tokens is actually part of the OAuth 2 standard and was widely adopted by companies like Google. The OAuth standard doesn't restrict you to the type of token that you use because it focuses on the overall flow of data. But back to the access token, it is used in place of sending your username and password directly to the backend of the application that you're using. So the authorization server is acting as sort of this intermediate step which grants you these temporary keys, this access tokens, which grant access to resources, so that the user never sends their password directly to the resource server. They only need to trust Google or whoever the authorization server is with their password, and the OAuth flow will do the rest. All right, I know this is a bit abstract, so let's look at an example in the next video. As we keep exploring, I promise it'll make more and more sense. I'll see you in the next one. Welcome back. Let's look at the OAuth authorization code flow in action. This is going to be a deep dive, so let's get into it. What really happens when I sign in with Google as my social provider on Medium.com? Let's explore in our developer tools by going to the Network tab and making sure that we're preserving the log, because we're going to be redirected a few times as we log in. Remember, the authorization code flow is based on redirects. So I'll clear the terminal and let's sign in. First thing, I'm taken to this screen where I can sign in with Google by putting in my email or phone number. And we're also being asked for consent for Google to share our name, email address, language preference, and profile picture with Medium. The first thing that happened is our browser made a request when we clicked on the Sign In with Google button to medium.com/connect/Google, which responded with a 302 redirect status code that redirected us, if we scroll down, to accounts.google.com. That's our Google authorization server, and specifically the OAuth 2/auth endpoint. This is the next request in our developer tools here. We're making a request to /auth, which is kicking off our authorization code flow. This is the first step where the web app makes a authorization code request to /authorize, or in Google's case, they've named it /auth. That's the first request being made against the authorization server. And just like our flow predicts, the response to this request was a 302 redirect, which is now asking us to authenticate with Google and provide our consent so that Medium has access to use our account to log in. Before we actually put in our information and see what the next steps are, let's look at these query parameters that we passed into the auth endpoint. When we kick off an OAuth flow by making this first request that we see in front of us, there's a bunch of data that we're passing in to Google so that they know what site is asking them for the login, and which also helps Google know what to do when the user logs in. So we can see that, among other things, we've passed in this client ID parameter, which identifies our application, as well as this redirect URI, which is where Google will redirect us once we've logged in successfully and given our consent. This redirect URI is sometimes called the callback URI because the authorization server, Google, will send the user to that location with some data as a way of calling our application back. And the data that Google will send us is based on the next two parameters. So we're passing in response_type equals code, which tells Google that we're using the authorization code flow and that we expect to receive in response this code so that our callback, when it's handled by our server by medium.com/callback/authenticate, can continue with the next steps of our flow. We'll see that in just a second, but the key is that we'll be getting back this code in the callback once the user logs in. In addition, we pass in this scope parameter, which asks for specific permissions that the client wants. We want access to specific data from the user, like their email and their profile, and also this OpenID, which tells us that we're not only using OAuth 2, but we're using this additional standard. We're using OpenID Connect when we're logging in to Medium with Google. The OpenID Connect protocol is built on top of the OAuth 2 protocol, and it tightens up OAuth a little bit and makes it a little bit more opinionated in exactly how you follow that flow. Because OpenID is more specific in which data is being passed around, it's often used by larger companies when they use OAuth 2. But it's a little bit beyond the scope of this course. We could spend hours and hours just talking about different slight variations on doing login. But the important part is that OpenID is built on top of OAuth. So everything we learn in OAuth still applies when we use OpenID. All right, so let's see what happens when we put in our email address into this sign-in dialog. We'll sign in with node-dev123 and click Next in our window. We're taken to this page, still in the authorization server, that is now asking us to sign in with a password. This part is not strictly part of the OAuth flow. We're still giving our authentication and consent inside of the authorization server. And the different steps for this are being handled by Google and their sign-on flow. We need to follow their steps before we can get this authorization code response in return. So let's put in our password and scroll down so we can see our request once we succeed. So let's check the next step. And we can see Google is making quite a few different requests. We're being redirected to first this check cookie endpoint, Hold on, let's see what was happening here. First, Google checked our cookies, and then we made a request against this setSID endpoint on YouTube. Hold on, why YouTube? And if we scroll down, we can see that this request set a bunch of cookies on the youtube.com domain. And then the next setSID endpoint here, the next request we made, was very similar, but this time it's setting a bunch of cookies on google.ca, the Google site for the country that I'm currently in. By logging in on Medium, my Google account is now signed in on all these different Google sites. Another benefit of OAuth and OpenID Connect is what's known as single sign-on. When I sign in on Medium with my Google account, in another window, I can now go to youtube.com and I'm already logged in. That's the beauty of single sign-on. When I sign in to a authorization server once on one website, I'm now signed in on all of the sites owned by that authorization provider. In this case, with Google, which owns YouTube. All right, back to our flow. After these setSID requests, we made a request to accounts.google.com/OAuth/consent, which is another step in Google's sign-in process. In this case, it's part of the step where we're getting the user's consent, which is very important. But we're still in this authentication and consent step. So let's see what happens after. We finally get a callback, check it out, to medium.com/m/callback/authenticate, which was the redirect URI we passed in when we kicked off this entire flow. And remember, we asked for the authorization code. And if we go through our query parameters here, let's see, there's our code. With this, Medium.com now has the data that it needs to complete the rest of the OAuth flow. And notice that we also got back the scope that we passed in with the email and profile, as well as some additional OpenID related things. And if we scroll through, there's actually no more steps in our browser's log before we were taken to the medium.com homepage with a successfully logged in user. What happened with the rest of the steps in the OAuth flow? Well, when we get this callback in our application, let's see what that corresponds to. We got our authorization code response. That's the code that's coming back in our callback. And typically, the next steps that happen here are performed on the server that corresponds to our web application. Why? Because with the authorization code response, our application now needs to send back the authorization code as well as the client secret to this token endpoint in the authorization server. So we need access to this secret value to make this request to get the token. And there's no good way of keeping a client secret actually secret if it lives in every user's browser. This client secret is general to the entire application. There's only one client secret per application. So we don't want our users to be able to read it, which is why we keep the client secret in the server side. So what's happened is that the Medium backend API is taking this request to the authenticate callback, and it's taking this authorization code, as well as the client secret that it knows, because the client secret lives in Medium's server, and it's making a request to this token endpoint in Google's authorization server, getting the response back with the access token, and saving that somewhere so that it can then be verified for each user request against our server. Sometimes the access token will be saved in our browser in something like local storage, or in our browser's cookies, or sometimes it'll be saved in the server as a user session. We'll discuss these details later in the section. The important part is that our authentication flow is now complete, and we have our access token. Finally, we're taken back to our home page as a logged-in user. In this redirect, notice that our callback is redirecting us. Let's see where. The location we're being redirected to is our Medium homepage. All right, what we've done is we've confirmed that the different steps of the OAuth authorization code flow apply when we sign in with Google. And we now have a better idea of the different kinds of data that's being passed around and how it's being handled. As you get more experience implementing these flows in your applications, you'll get much more comfortable with the steps involved. All right, let's take a well-deserved break and keep going in the next video. I'll see you then. Bye for now. It's time to get some practice implementing OAuth in our own applications. Let's implement social sign-on using Google in our Node servers. The first step will always be registering your application, your client, with the authorization server. In this video, let's register a Node web application using Google as our authorization server, so that we can use Google social sign-on, just like we've seen in many of our favorite sites. To register an application with Google, we need to log into our Google account and go to the Google Developer Dashboard, which I'll link to in this video. Or you can do a search for OAuth Google, and most likely the first result will take you to a page that explains how to get the OAuth client credentials. So you can also click on any link that points to something like the Google API console, which will take you to a page that looks something like this. We'll start by going right here, where you might want to create a new project for our Node application. Let's call it Node Application. The most creative name possible, I know. And I'll click Create. With our Node application project set up, we can go ahead and get that application registered with Google as the authorization server. And by the way, you can do all of this with any Google account. There's no need to pay to use Google as a social sign-on provider. The way we register our application as a client with Google, first of all, let's make sure we're using the project that we just created, just in case we have existing projects. And we'll go to this Credentials tab right here. We have the option to create API keys for different Google services, But we also have this OAuth 2 section. So let's create some OAuth credentials. Most importantly, the OAuth client ID, which uniquely identifies our application to Google. Because there are thousands of different applications that all use Google as an OAuth provider. So we're going to create our own OAuth client ID, which we can see is used to identify a single application to Google's OAuth servers. And Google tells us that before we continue, we first need to set a product name so that Google knows what to display in that consent screen that the user sees when they give consent to Google to give our application access to their basic profile information, like their email. So we'll configure the consent screen. And here, if we want to make our application public, we'll always select external as the user type. If we were in a Google organization, we could limit login to only users within our organization by selecting internal. But in this case, we're not part of a Google workspace, so we'll select external and create. This is where we put in all of the information that will show up in that consent screen, which notifies the user logging in for the first time that our application wants to access their Google account so that they can log in. What we put here under app name will be what shows up on that screen. So I'll call it node example. And our user support email will just be the email of our account. If we wanted to, we could upload a logo for our application. And finally, here under app domain, we can optionally choose to include a link to our application's homepage, a privacy policy, as well as our terms of service. For now, we can scroll through this past authorized domains and just put in our developer contact information, again using the email for our current account. So I'll put that in. And let me just make sure that's the email for the account. That looks correct. So we'll save and continue. On this next screen, we can select the scopes available to our application. To recap, these scopes give our application access to specific data about the user account that just logged in. So if we go to add or remove scopes here, we have the option to add various different types of information that's going to be returned from Google when a user logs in. And this data is going to be available in our application. For example, to pre-populate any profile information, we need to declare it ahead of time because it's going to be included in that consent screen. The user logging in needs to give consent to share whatever information about their account. So for our example, let's select just the user's email to their Google account. But we could also select their profile information, as well as this OpenID scope if we wanted to use OpenID Connect, that additional standard on top of OAuth. We're okay with just the email. So let's go ahead and update our scopes. We can see it was successfully added under non-sensitive scopes. And now we can just scroll down and save and continue. We can add test users that will be able to log into our application before that application has been verified by Google, which is something we can do once our application is ready to be published in production. In testing mode, only users that we add here will be able to log in to our application. And if we save and continue on this screen, we're presented with a summary of the data we put in. And we can go back to the dashboard and publish our application. What does this do? Let's see. We can push to production so that any user with a Google account can log in. Remember, we start off in testing mode, where only a certain set of whitelisted test users will be able to log in to our application, which is useful in some cases, but for us, we're okay with skipping to production login. Because we're not requesting any sensitive data from the user's profile, when we selected those scopes, we can skip this verification step, which makes our life a lot easier. So we can go to confirm, and our Node example app is ready to go. What we do now is we go to our credentials page, and finally, with our OAuth consent screen taken care of, we can create those credentials, including our OAuth client ID. So I'll go ahead and do that. We'll select our application type. We're not a desktop app or an iOS app. So we'll just go ahead and select Web Application. And again, we can name our OAuth client. So let's go ahead and use the same name we used in the consent screen. So Node example. All right, and we're nearing the end. This step is important. We need to set the authorized JavaScript origins and authorized redirect URIs that Google will allow to log in using Google as the authorization server. If we're working on localhost, in development, we would need to add localhost as an authorized JavaScript origin by going to add URI and writing in the exact path, the exact URI for our front-end application that's going to be logging in using Google. So it could be something like HTTPS localhost on port 3000. We have to make sure to get this correct, or else our login flow won't work. For now, let's go ahead and add localhost on port 3000 using the HTTPS protocol. And if we had a test or production environment that's available at some URL, we would add that here as well. And then for the authorized redirect URIs, we would add the URI for the endpoint in our server that's going to be handling the authorization code. Remember our OAuth flow. When we make the initial request to the authorized endpoint, or auth in Google's case, we pass in, among other things, a redirect URI, which is where Google, the authorization server, will redirect the browser once the user has authenticated, they've logged in and consented, and the authorization code response is ready. So this response here goes to the redirect URI. And that's what we need to specify in this field for development as well as production if we deploy our application to some domain. Let's define an endpoint that's going to handle our redirect. It's going to be at HTTPS on localhost, and our front end and back end will be on the same server, port 3000, and our back end is going to handle authentication related requests under the auth path, which might support different OAuth providers, for example, Google for social sign-in, but maybe also GitHub. So we'll specify that we're handling Google's authentication, and the endpoint is for our callback or redirect URI. So we're going to need to define this endpoint in our Node application. All right, let's add that redirect URI, and we can get rid of these empty items here and create our OAuth client ID. Success! What Google now gives us is our client ID as well as our client secret, which we'll add to our server when we configure it. This secret is what's used to make sure that only your application with the secret will be able to grant authorization. Because of this, we want to make sure this value is kept secure. So we can go ahead and copy these values and save them somewhere. Or if we click OK, we can always get these values by clicking under our application name under OAuth to client IDs. And if I zoom out here, our client ID is right here on the right, and our client secret is right next to it. These are the values we need. All right, that was a lot of configuration, but we're finally ready to start coding. Let's take a well-deserved break, and I'll see you in the next video. Welcome back. We're going to add Google Sign-On into our security example project, which is being served over HTTPS. And we're going to protect the secret endpoint so that only authorized users can access the data that it provides. Normally, when we want to protect our endpoints, when we want to restrict access to them to only logged in users, for example, we do this in middleware that runs before our request handler has a chance to send that data back. Just like the Helmet middleware helps protect all of the endpoints that come after it, if we wanted to restrict access to all of the endpoints in our API, well, we would add an app.use with some middleware. So that's a function that takes request, response, and a next function. And in this function, we would return an error code, maybe 401 if the user is not logged in, or 403 if they don't have the right permissions. And if all of our checks that the current user has access to our API pass, then we'll just call next and allow the request handlers for the appropriate endpoint to run. So we would do something in this middleware, checking some, say, is logged in Boolean if we wanted to restrict our API only to logged in users. Let's set this to true for now and add ourselves a to-do. The way our middleware would work is we would check if is logged in, and if the user is not, then we would return that error code. So res.status, they're not logged in, so that's a 401, and we could send back some information, so say a JSON object, with an error message saying you must log in. But if the user is logged in, then we'll just call next, and they'll have access to the rest of our API. But here's the thing. We want to restrict access only to certain endpoints, only to our secret data, and not to our HTML, which is also being served on our API. So rather than running this middleware before all of our endpoints, what we can do is let's move this middleware function outside of our app.use statement and instead assign it to a function. So we'll say function, and what our function will do is check if a user is logged in. So checked logged in, and we'll paste in the function we just wrote. We're not using an arrow function anymore, so we can remove that. And now, because we have a reusable middleware function, we can restrict access just to the secret endpoint by passing that middleware in before our request handler. So by just saying check logged in, our middleware function, and then comma with our final request or endpoint handler. In Express and similar frameworks, you can pass in middleware for each endpoint individually when you define the route. I could add as many pieces of middleware into this endpoint as I need, and they would all run in sequence before the response was sent. So I could add another function, say check permissions, that checks that the logged in user has certain permissions, like, for example, being an administrator, and any incoming request would need to pass both of these middlewares before continuing. This is how we restrict access to our APIs. This is how we do authorization in Express. All right, so for now, let's just check that the user is logged in. So we'll remove check permissions, and we'll say that all logged in users are authorized to access the secret value. Now, what other endpoints do we need? Well, the first one might be obvious. We need to let the user log in before any check has the chance to succeed. A login endpoint is just like any other. It's usually a GET on some route, say under Authenticate or Auth, which is where we'll have all our auth-related endpoints. We're doing Google OAuth, so we're going to specify that this is the Google login to authenticate. And for now, we'll leave this function empty. We'll just say rec res, and it returns nothing. To start, it makes sense to think from a higher level which endpoints we'll need, and start from that top level and work our way down. We already agreed on our next endpoint. When we registered our application with Google, we specified that there would be a GET endpoint under /auth /Google /callback. Remember that? The callback URL is what specifies the redirect from our authorization server, that's Google, when it sends back the authorization code, which is what we use to get back that access token, which we use in all of our requests to gain access to restricted data in our application. The callback URL, where Google will send this authorization code, lives in our application, specifically in our backend API. All right, so we'll start by making this a placeholder request, just like above, so that Google's authorization server has something to call back. What other endpoints can we add? Well, if a user can log in with some provider like Google, they should be able to log out as well. To log out, the user doesn't need to pass in any data. So again, we can make this a GET request, and this time, we'll put it under our auth endpoints. It's related to authentication, but I'm going to use my knowledge of how we're going to implement authentication and say that the way we log out is generic. It's not specific to Google or Facebook or any other OAuth provider. The way we log out is going to be the same regardless. So we don't need to prefix it with Google. We can just say auth/logout and add that as a placeholder as well. Things are looking good. This is very much like any OAuth application will look. Before we move on, let's think for a second about how we'll be using these endpoints. In our very bare bones index.html, the basic purpose of our application is to display the user's secret. So let's just start with, here is your secret. And to access it, the user is going to need to click on some link. So I'll add a href, which points to that secret endpoint. The backend and the frontend are both on the same server, so I can just say /secret, and that's where the user will go if they demand to be shown that secret. The user is saying, show me, but they'll only have access if they're already logged in. So the next link we'll add here is going to be to the login endpoint, which we just added under /auth/Google, and that's going to be the Google login. And last but not least, we're going to have the logout button, which will log the user out regardless of how they signed in. Even though for us it'll be Google, the way we log out in general applies regardless of which provider we used. So our link is going to be to auth/logout, OUT, and that's going to be sign out. There we have it, the overall skeleton of an authenticated, secure application. Let's just make sure things work. npm start. And in our browser, we need to make sure, remember, our server is hosted using HTTPS. So let's see what's being served. We might need to pass this certificate warning because we're running a self-signed certificate. So I'll proceed. And it looks like things are working. The only problem is that anyone, even before they've logged in, can click Show Me, and they'll get access to our secret. Let's find out how to actually log in and restrict access in the next video. I'll see you there. Welcome back. How are we going to actually log in the user with Google, following the OAuth flow? As we've seen, there's quite a few steps involved in the OAuth process. So how are we going to do all this? We're going to use a widely used middleware called Passport.js. What is Passport? It's an NPM package that provides authentication middleware for Node. It serves just that one purpose, but it's been downloaded many millions of times because it does this really well by covering hundreds of different approaches to authentication. As we've seen, authentication can be fairly complex, but the beauty of Passport is that it exposes a common way, a common approach to doing authentication regardless of which provider, which standard, or which flow you're using. It does this by using these plugins, these packages that plug in to Passport. And it calls these packages that work with Passport strategies. We'll see just how this works in a second. But Passport includes strategies for just about any login system you can imagine. Whether it's using passwords or tokens, Twitter or Facebook, or even Google, chances are someone has created a Passport strategy that we can reuse. We're using the OAuth 2 framework with Google. So let's look up OAuth 2, and the first result is this Passport Google OAuth 2.0 authentication strategy, which seems to be very widely downloaded. There's this other Passport Google OAuth 2 strategy, but it seems less popular. So let's go with the widely used, probably better supported version right here. Let's load that strategy in our browser. And what we're going to do is npm install it in our project. The name of this strategy here corresponds to the name of the npm package where it lives. Back in our security example, let's npm install the strategy that we just found, as well as the main Passport project. We'll need both running in combination to do our Google OAuth social login. So npm install Passport. There we go. We're ready. Let's find out how to put Passport to use in the next video. We're going to see just how easy Passport makes our lives. I'll see you then. Welcome back. How are we going to connect our Node application with Google so that Google knows our application is the one requesting users to log in? How does everything fit together? If we log into our Google account and we go in our Node application example project to our credentials page, the way everything fits together is using this client ID and client secret. That's how Google identifies our application and keeps the access tokens we create secure. So let's copy in this client ID value and the client secret into our Node project. Where do we put these values? Let's see. We can start right next to where we assign the port number by creating an object where these values go. Let's call this object config. It'll store our configuration values, and we'll create an object where the client ID is set to this value that we just copied. Now, when you copy this value from Google, make sure you're copying exactly what Google shows, and just remove any added white space from when you were copying that value over. The value needs to match exactly for Google to allow you to log in, and getting the value wrong will cause confusion down the line. So make sure this value here matches what's in your Google dashboard exactly. And if you have any issues, just double check. All right, so let's add that client secret as well. I'll copy the value from there and into our Node application, adding a second value, client underscore secret, and assigning that to this secret value while removing white space. And I need to add a comma here. All right. But wait a second. Does this look right to you? We're following security best practices, right? And it's not very secure to keep our secret values in our source code, which we might be sharing with others or publishing somewhere, like on GitHub. In fact, it's never a good idea to have secret values inside your source code, because that makes it easier for these values to be mistakenly leaked. And it makes our lives easier when we deploy our applications to take these values from some configuration file or from the environment where the application is being run, so that they can be set and secured separately from your application's source code. The most common approach to solving this problem in Node is using the .env npm package. What .env does is it loads environmental variables from a .env file into this process.env built-in value. Very simple. It loads .env into this one value so that the values, the secrets in your environment, can be accessed from your source code. This is great, especially if you have multiple environments, like a development environment alongside a testing or production environment, which each need different secret values, or even non-secret configuration values, for example, a database URL that points somewhere else for development versus production. In that case, you might split your environment into a dev.env file as well as a prod or production.env file and load the appropriate one depending on which environment your code is running in. The .env package helps with all this. Not only does this help make your application more secure, if you treat these .env files as private, but it also helps make your servers, your applications, more configurable. It separates the logic of your program in the source code with the configuration values. All right, that's enough about .env. Let's add it to our project. I'm going to npm install .env. Now, the way we use this package is near the top of our program, requiring .env and calling the .config function. We don't need to assign .env to a constant because this function is all we'll be calling. And what it does is it takes all the values in your .env file, which for us is going to store the client ID and secret. So let's copy those two values and move them into .env, where we need to change the formatting here a little bit because our .env package expects values not as a JSON object, but instead as just this pair of the value's name, the key, and then the equal sign, followed by the value directly, without any quotes or commas. So let's do the same for our client ID and remove the comma and quote. Again, make sure you're not removing too much because we need these values to match exactly. And with our values now in a format that's recognizable, our server.js can now take the client ID in our config object, so client ID, and set it to the value that is being set by .env. So that's process in our built-in process module .env.client ID. And let's do the same for client_secret. Process.env.client secret. Very nice. Now remember, we added our value to this .env file to separate it from our source code, but also to prevent it from getting leaked mistakenly. Which means if we're publishing our source code on a repository like Git, we want to make sure that any of our environment files aren't being published to our source code repository. So if we have a git ignore file, let's add .env to that file right now. And that file will never be published to Git. Much better. All right, let's put our client ID and secret, which are now being handled securely, to use in the next video. It's going to be a good one, so I'll see you in the next one. Welcome back. We've registered our application with Google. We now have access to our client ID and client secret in our source code, which means it's time for us to add login with Google and OAuth into this application, the same way we would for any Node application that uses OAuth. Let's jump in. We've now installed the Passport npm package along with the Google OAuth 2.0 Passport strategy. So let's take these npm packages and import them in our server.js. I'm going to create const passport, which equals require passport. And right below that, I'm going to take this strategy value from the Google OAuth Passport module. So require, passing in the name of the module that contains the strategy, which will plug in to Passport. How will that look? Well, Passport is middleware. So it's always a good idea to start our servers that use Passport by adding one middleware somewhere near the top of our middleware chain. Passport is security related, so we'll add it right below Helmet, which is securing all of our endpoints by protecting against common configuration issues, whereas Passport will help us authenticate users. So we're going to say app.use passport.initialize, which is a function that returns this Passport middleware that helps us to set up Passport, specifically the Passport session, which is something we'll talk about later in this section. Now, probably the most important piece of Passport setup that we'll need to do once Passport has been initialized is setting the strategy that Passport uses, which we need to do somewhere before our middleware chain. So right here below config, I'm going to set the Passport strategy, which determines how Passport authenticates users, by saying Passport is using, with the use function, some object that follows this strategy pattern that Passport relies on, just like the one that we're requiring from our Google OAuth module. So I'm going to initialize that Google OAuth strategy by constructing that strategy with new strategy, which takes in some parameters. The first is this options object, and the second is this verify function. Let's start with the options object. We're using OAuth here, and Passport is going to help us go through this OAuth flow, so we don't have to keep track of all of these requests to the Google servers and how we respond to them. What does our web app need to do? Well, it needs to kick off the OAuth flow with this authorize request, and then it needs to handle the authorization code response that comes into our callback URL as a redirect. It needs to send that authorization code and this client secret to some endpoint in Google, which will give us back an access token, which is finally what our app needs and what can be associated with a user when they try to access some protected resource in our application. That's the recap. What this all means for us is that it makes sense for our Google OAuth strategy to need to know the callback URL so that it can send that to Google, which will then know which endpoint in our server here, this auth/Google/callback endpoint, Google needs to send that authorization code to. So we're going to take this endpoint and set it as the callback URL, /auth/Google/callback. What else does Google need to know? Well, it needs to know what our client ID is. So that's config.clientID, which will identify our application. And we also need to set this client secret. So client secret so that it can be sent to Google when we're converting that authorization code into a token. Remember, that request requires us, the web app, to send both the authorization code we get in the callback URL as well as this client secret. So let's set that as well, config.clientSecret. And we can clean things up a little bit and move all of these options into a const auth options. So that's going to hold everything we need to pass into our strategy here, which will take auth options. And the second parameter there, that's the verify function. This is a callback function that is called when Passport authenticates a user. When we're authenticating a request to our API, Passport parses the user credentials contained in that request, and it then calls this verify function, this callback, with those credentials as arguments. Because we're using OAuth, the credentials for our user include the access token and potentially this refresh token, which can optionally be used to get new access tokens when the access token is about to expire. So refresh tokens are a way of extending the time that a user's login is valid, so they don't have to keep logging in. We can also see that the verify callback takes in the user's data in this profile object, as well as this done callback, which is called if the credentials were passed are valid. Instead of just talking about this, let's see this in action. We're going to pass in a verify callback function that we define right above our passport.use statement. So function verify callback is going to take in, just like we saw, the access token, optionally a refresh token, which we can ignore if it doesn't exist, the profile, and this done callback. And inside of this function, we'll have access to all of this data once the OAuth flow has been completed inside of the Passport middleware. So we can choose to log any of this. We don't want to log our credentials because that might cause them to get leaked, but we can log, for example, the Google profile that we get back once a user is logged in. What the verify function does at the core is if the credentials that were passed, so the access token and the refresh token, if those are valid, we call done to supply Passport with the user that authenticated. And if something goes wrong, or the user's credentials are invalid, we can pass in an error as this first option, but in our case, there's no error, and the user data for our successfully authenticated user is just this profile object. So when we pass profile into the second parameter of this done function, Passport now knows that this user is logged in. Now, you might be asking, what's the point of this verify callback if we're just passing back this profile object that was already passed in to verify callback? Isn't this just passing our data straight through? Well, with OAuth, if we've received an access token, we know that the credentials for that user are valid. Google has already checked that for us. But if we were checking passwords ourselves, the user's password is what would come into this verify callback. And this function is where we could compare the user's password against some value in our database and decide whether the credentials that are being passed in are valid or not. As an added bonus, if we are using a database, we can also use this verify callback function to save the user that's come back as well as any of their profile information into our database so that it's available in the rest of our application. The verify function is responsible for wrapping up the authentication process. It just so happens that with OAuth, most of the heavy lifting has already been done. We're almost there. Let's take a short break, and in the next video, let's implement that callback URL as well as the actual login endpoint. We've done most of the hard work already, so let's wrap up and see everything in action. I'll see you in the next video. In the last video, we set up our Passport Google OAuth strategy and created the verify callback, which is called when a user is authenticated. Now, let's take a look at this callback URL and the endpoint to actually log a user in. Starting from this callback URL, this is a key part of the OAuth process. The Google servers need to be able to call this /auth/Google/callback endpoint so that an authorization code can be exchanged for an access token. Luckily, Passport has us covered. Instead of writing out this route handler for the callback ourselves, we can use a function in Passport called passport.authenticate. As a parameter, we pass in Google so that Passport knows we're using the Google strategy to log in. The second parameter here is an options object, where we can pass in what happens if we fail to authenticate and what happens if we authenticate successfully. We do this by passing in this failure redirect, which specifies which path in our server, in our application, we want the user to be redirected to if something goes wrong when they're logging in. And we can set this success redirect to redirect the user to some page if they've logged in successfully. So for now, let's say if they log in successfully, we take them back to the root of our application. And if something goes wrong, if they fail to authenticate, let's take them to this failure page. And for now, let's just add this failure endpoint. So we'll say app.get/failure and just say that this takes the request and response and returns back a string. So return res.send failed to log in. All right, so the user will see an error message if something goes wrong, and if not, they'll be taken to the home page as a logged in user. We'll also set this session property to be false for now, just so we don't have to deal with sessions to test our code in this video. We'll re-enable sessions very shortly in an upcoming video. But for now, this will make our lives easier. And I've noticed that this parenthesis shouldn't be closed when we write Google. It needs to be closed right here when we finish passing in this options object. And then this third parameter here is going to be our request handler. So it takes in a request and a response. And here we can optionally choose to do something additional when Google calls us back. For example, we could do a res.send here, or we could do res.redirect ourselves instead of using these failure and success properties in our authenticate middleware here. But for now, I'll just use this to log that Google called us back. Yay. All right. And let me clean this up a little bit so it's more obvious that these are middleware over here. So I'll indent this, and then we'll have our request handler on the line below. Something like that. Looks pretty good. And that's it. This Passport Authenticate middleware, where we pass in the failure and success redirect, will handle this entire flow from when Google sends us the authorization code response and our request back to Google to get the access token, as well as Google's response to that. 3 steps all in one. That's the callback endpoint. Now, how do we kick off this entire process? Remember, when we click sign in or Google login in our front end, we're taken to /auth/Google, which is supposed to start this entire OAuth flow. Well, there's good news there too. We can use this same passport.authenticate middleware for the first step of our login process as well. We'll replace this request handler and just say passport.authenticate. And again, we need to specify that this is the Google strategy. And this time, instead of passing in these redirects, in this options object, we instead specify what we want the scope to be. Remember, the scope specifies which data we're requesting from Google when everything succeeds. So here we can pass in the data that we need. So we can say, for example, email. And potentially we could say profile as well. Any data that we need to, for example, fill out our user's information in a database. For our purposes, let's keep things simple and just ask for the email. And guess what? That's it. That's login using Passport to help us with the Google OAuth flow. Let's see everything in action. Hopefully we didn't make any mistakes. Let's do npm start. In our browser, let's navigate to the root of our application. And let's open the network tab of our developer tools so that we can see what requests are being made and if we're actually following that OAuth flow. Moment of truth, let's go. Let's Google login. So far, so good. We're taken to this sign in with Google page. Check it out with the OAuth flow starting at our /auth/Google page, which then redirected us to this accounts.google.com domain under the OAuth2 path and the auth endpoint, where we pass in the response type, that's code, because we're following the authorization code flow, where there's a server and a front end. We're passing in our redirect URI, which points to our Google callback here. We're passing in the scope correctly, as well as our client ID. And because we did all of this correctly, well, we're taken to this page, which shows the name of the application we registered in Google, and we can even see the consents that we need to agree to. So Google will share our name, our email address, language preference, and profile picture with our Node example application. Very cool. Let's open that network tab back up and see what happens next. I'll log in with my Node Dev account and click Next on this form. We can see the Google sign-in process is continuing. We're now at this account lookup step, which succeeded. And we're now asked for our password. So let's put that in. And click Next on this form. check it out. We're seeing these check cookie and set SID requests, just like we saw when we went through the OAuth flow the first time. And finally, Google redirects us to our callback URL. In that redirect, Google included that authorization code value here, and our Passport middleware did the rest. Passport exchanged the authorization code with the client secret that it knows, the one from our .env, and it exchanged those values for an access token, and that access token, along with our Google profile information, was sent back to us where? In our verify callback. We're not logging the access token, but it's now available to our application. But we are logging the Google profile. We can see what data Google made available to us because a user successfully logged in. We can see the logged in user's email, that it's been verified. We have the user's Google ID and potentially a display name, if one has been selected, as well as the user's profile photo. And just like we specified in our success redirect, when everything completed, we were sent back to our home page. Really great stuff. Just like that, Passport has helped us complete the entire OAuth login flow. From the initial request to Google, all of the login steps and consents, as well as all of these steps to get back this access token when a user successfully authenticated with Google and logged in. All that remains is for us to make logged in requests to our application and get back the response in any endpoints that require users to be authenticated. With a little help from Passport, we've come really far already. Let's keep it going in the next video. I'll see you then. Welcome back. What about cookies? Cookies are something you'll see very often as a web developer. But what are cookies? You might already be familiar, but even if you are, there's probably a thing or two you haven't considered. Let's start from the basics. Cookies are basically strings of data that are stored in your browser. In Chrome, we can see our cookies by going to Application in our developer tools, and on the left here, different ways of storing data in the browser. So there's local storage and session storage. There's potentially a few different ways of storing data in a database. But the most widely used mechanism is cookies. These are values that are usually set by the server, which are sent to the server anytime your browser makes a request to that site, for example, Google. So cookies are a way of storing data in your browser that gets sent to the server whenever you make a request against it. They're sent automatically without you as a developer having to do anything when you make that request. These values have names, they contain a string, and are associated with some domain. Optionally, you can also set a cookie that will only be sent for a specific path in that domain. Cookies also have an expiry date and some properties like HTTP only or secure or same site that help secure that cookie. For example, secure cookies will only ever be sent when you're talking to that domain over HTTPS. And HTTP-only cookies live in your browser but are not accessible from JavaScript code, which means the server has more control over the value in that cookie. This is to prevent certain security issues, like what's known as a cross-site scripting attack, where a hacker manages to load some JavaScript into your browser that's executing on a site you trust, like Google, and can then execute that code with all of your permissions and access to all your data for that site. But now, because we've set the HTTP only flag, even with full access to JavaScript, that malicious code, that cross-site scripting attack, won't have access to the value in your HTTP only cookie. As we'll see in a second, this is important because our cookies can store sensitive values that we want to keep private. Just like we had token-based authentication, we can also do authentication with cookies. To recap, with token-based authentication, where a browser authenticates with a server by checking that the user's username and password match, at which point, if the server agrees that this matches a known user's credentials, the server will send back some access token in the response. For example, a token that follows the JWT standard. And it's then up to the browser to send that token in every request that it makes to the server, so that the server can validate that token by checking that, for example, Larry here authenticated to the server, his password matched, and this token belongs to him, so we can give him the data that he needs in the response to his request. But with token-based authentication, that token needs to be sent in this header, this authorization header, by the developer each time you want to make an authenticated request. We could do authentication using cookies instead. The authentication step would work in much the same way. The server would make sure that the user's credentials, their username and password in this case, match a known user, but rather than sending a token in the response, the server sets this cookie value, which can store different bits of information, even an access token or a session identifier. This would be some data that uniquely identifies the user currently browsing your server, your website. These cookie values are set when the server responds with this set cookie header, which the browser knows means that these values need to be stored in the browser's cookies. From now on, that cookie value will automatically be sent by the browser whenever the browser makes a request against the server. It will set this cookie header with any of the values that have been set by the server previously. Instead of looking in the authorization header, the server can now look inside the cookie, check it, and see, okay, I know who the user is, they've already authenticated, and they're allowed to access this user data. So I can send the response with their name. Both cookies and tokens sent in the authorization header provide two different ways of passing authentication data to the server. They're both often used to prove to the server who is browsing that site. But to really understand these use cases, we're going to need to talk about this session and really understand what that means. For that, I'll see you in the next video. Welcome back. Let's take a moment to talk about sessions. This is a topic that is definitely going to come up when you're building a large authenticated website. So what is a session? Sessions are a way of storing data about the current active user. This could be something like the name of a user or what page of a site they last visited. However, Usually, public data like a user's name can be stored on the client side in the browser without worrying about any server-side session. There's no reason to keep this data secure. On the other hand, what should definitely live in a session is data that we wouldn't want the user in their browser to modify. So what kinds of data do we not want our users to change? A user's bank balance, the amount of money they have in their bank account, or their permissions to access data in the server. For this type of information, the client can have access to it, the client can read it, but if we're a bank, we don't want users setting their own bank balances. That would be a disaster. This is the data that we most often need sessions for, when we want to keep track of state that shouldn't be changed by the user in their browser directly. Now, if this sounds a lot like what you would use a database for, well, you're absolutely right. However, sessions are usually short-lived. Sessions capture the state of an application during the time that a user is interacting with it. The data in a session is what is relevant to a user as they're using the application until they quit or log out, whereas the data in a database is more permanent. To use another example, if you're on a shopping site, the current items in your shopping cart might be in a session, while your order history might live in a database that persists through many sessions. The database sticks around regardless of who's logged in or which browser you're using on which machine, whereas sessions tend to be tied to a specific browser and the temporary state of the application on that browser. If this sounds a bit theoretical to you right now, I don't blame you. Let's look at an example. Let's find out how we actually work with sessions most often. For that, I'll see you in the next one. Welcome back. To recap, we use sessions to store temporary user data as that user is using our application. Sessions are most often used to store data about the current user who is logged in to our web application in their browser. Let's explore that in this video. But first, how do we store session data? We store sessions in one of two ways. We can have server-side sessions, where user data lives in the server on a database somewhere, and the data would get looked up for each request that the user makes, and potentially deleted if the user logs out or quits their browser. The alternative is to have a client-side session, where we store session data in the browser, specifically in the browser's cookies. In fact, cookies are almost always used to implement sessions, although we do things slightly differently in the cookie depending on if we're using this client-side session or a server-side session. To really understand this, let's look back at our cookie-based authentication example. Depending on if we're doing server-side sessions or client-side sessions, we'll be using cookies in one of two ways. We'll either be using stateful cookies or stateless cookies. Let's start with stateful cookies. When using cookies for authentication, once the user authenticated with the server by putting in the correct password, the server responded by setting a cookie that stores this session identifier. This is what's known as a stateful cookie, where the cookie value, this session ID, is just a reference, a pointer to some session information that lives in a database somewhere in the server. So we use these stateful cookies when we're doing server-side sessions. With stateful cookies, we require a database to store our session data, and our server needs to look up the session in that database for the user identified by the session ID. This is great if we already have a database and we know really well how to manage data in that database, but it requires an additional request from the server to look up what data is actually stored for this user. And it can be more challenging to scale when you have many users, and each time you need to look something up, you're doing a read and a write to that database, which adds load to your server. Now, on the other hand, if you're doing stateless cookies and client-side sessions, all the session information that you need lives in the client already. It's stored in the browser's cookies. Each piece of session data corresponds to one cookie value. In this case, the server can still trust that the cookies haven't been tampered with as long as the server signs the user's cookies before they're sent to the client. Say we've logged in to the server. What this means is that we've put in some credentials, the server has validated them, and has now told us, okay, you're authenticated as a user with some specific user ID. The server can send back the user ID that's been authenticated and store it in a cookie that lives in the browser. To prevent the user from tampering with that cookie and saying that they're logged in as another user, for example, the server can encrypt or at least sign that cookie value using a secret key that only the server has access to. Now, if a browser without that key tries to modify the cookie with the session, when the server tries to read that value, it'll know that cookie is invalid and has been tampered with, and not authorize the user to make whatever request they're making. There's different benefits for doing client-side sessions and server-side sessions. If we're really concerned with keeping the data in our session a secret, we can keep this session on the server side, in a database that's not directly accessible to users. However, in the vast majority of cases, it's enough to ensure that the session data isn't being modified or tampered with. For example, if we're playing a game, we're okay with the user reading their own score. But we don't want the user to be able to give themselves a high score just by modifying their session data directly. Or if we're logged into a banking application, we're okay with seeing who we're logged in as, but the bank doesn't want us to be able to change who we're logged in as. That would give us the ability to transfer balances from strangers' accounts into our own. In the vast majority of these cases, we don't need to keep the session in the server. The session can be available in the browser, and as long as the server signs that cookie, the server will always know whether that data is valid. Remember, only the server has the key to sign the session. We'll see this in action in just a bit. However, there are some nice advantages to taking this approach. We simplify our backend because we no longer need to talk to our database and manage the data there. Instead, it lives in cookies that live in each user's browser. And we save ourselves from making that additional database lookup for each request, which means it's much easier to scale our servers. We just need to make sure that our session information isn't too large, because cookies are often limited in size by browsers, usually to about 4 kilobytes. For very large sessions, it makes more sense to use a database and server-side sessions. But usually, your session will include basic identifying information about the user who is currently logged in. So client-side sessions work just fine. All right, we've talked about quite a few different things in the past couple of videos. Let's take a little break and start looking at how we might apply these ideas that we've just been introduced to. It's going to be a good one, so I'll see you in the next one. Bye for now. Welcome back. We're almost done. The last part that we need to figure out is how to remember that the user logged in our application. Once we know whether a user is logged in or not, we can use this information to determine whether they're authorized to access some data, whether they're allowed to make a request against one of our API endpoints. To remember that our users are logged in, we're going to use a session. And because we're using Express, there's 2 main NPM packages that we have the option of using. Okay, I lied. There's actually hundreds of options, but these are the 2 that you need to know to understand what choices to make. There's Express-session and there's Cookie-session. Both of these are very common, and they're both part of the Express.js organization and the Express.js project on GitHub. However, they live in these separate NPM packages so that we can pick which approach makes sense for our application. Express-session is for server-side sessions, whereas Cookie-session is for client-side sessions. Let's see exactly what the difference is and decide which is more appropriate depending on which kind of application we're building. We'll start with Express-session because this is the most widely used simple session middleware that we can get for Express. This is middleware that stores session data on the server, just like we do whenever we do server-side sessions. It still uses cookies, but it only saves the session ID in the cookie itself, and not the session data, which might include things like the user's ID and their permissions. The session data itself lives in a database on the server, and our Express session middleware plugs in with many different types of databases. We can scroll down to the section here on compatible session stores, databases where you can store that session data that you don't want to be modified by the user. We can store our data in Apache's Cassandra, or scrolling down in a MongoDB-based session store. And there's many different variants of the SQL database that are supported as well. There's Postgres. By default, though, the Express Session middleware uses in-memory storage, which will get erased whenever you restart your server process. And it won't be shared if you have a cluster of processes running your server. So the default in-memory storage of the Express Session middleware is not intended to be used in a production environment. In production, you'll need to set up your own scalable session store from that list that we just saw. In comparison, the cookie session middleware stores the actual session data inside the user's cookie that's being sent back and forth from the browser to the server whenever you make a request from that browser. This cookie stores the entire session instead of just the session key or the session ID. The benefit is that it's simpler. We don't require a database where we need to look up all of our session data each time a request to our server comes in, and it helps keep our node process stateless so that we can scale it in a cluster using what we called load balancing. Now, there are some downsides. These cookie sessions or client-side sessions need to be small. They can't contain much data because the browser limits the size of your cookies in most cases, usually to around 4,096 bytes. And not only does the browser limit the size of your cookie, it's also a good idea to keep this cookie small because this is data that's going to be sent in every request. So we don't want to waste too much bandwidth, too much network traffic, passing in these large sessions with data that we don't need. Usually it's enough to just identify which user has been logged in and authenticated. The server can do the rest. And also, we need to be very aware that the data in our cookies is going to be visible to the client, to the browser. So if there's any reason to keep this data from our session a secret, then the Express Session middleware is probably a better choice. However, for our example, we're going to use cookie-session because it simplifies scaling, meaning we can have multiple instances of our node server running, each handling different requests. And we don't need to introduce a database to accomplish this, to keep our server stateless. Any session data we need is going to be available directly in the cookie. The server itself can remain stateless. It doesn't need to remember anything. These same benefits apply to real-life production systems. If security is the absolute most important thing that you're worried about, server-side sessions and the Express-Session middleware are probably your best bet. But in the majority of cases, it's not a requirement to keep the data from your session a secret. It's enough to sign that data using a key in the server to make sure that it isn't being tampered with. Right? Think back to the example we talked about of a banking application where the bank doesn't want a logged in user to edit that cookie and say they're logged in as another user, in that case, they could transfer anyone's bank balance to their own. That would be a problem. But having the user know who they're logged in as isn't really a problem at all. We'll see exactly how all this works in code in the next videos. However, the added benefit for us of using this package is that we get to learn about keeping our cookies and the data they contain secure. For example, we'll learn how to sign our cookies and make sure that they can't be accessed from JavaScript. The good news is the cookie session middleware helps us do the right thing. So if I scroll down here, under cookie options, we have, for example, the HTTP only flag being set to true by default. So our middleware is helping us make the right choice by making sure that the data in our cookie won't be available to client JavaScript, helping to protect us against scripts that try to steal the data in our cookies with those cross-site scripting attacks. And for example, we can set our cookie to be secure to make sure that the cookie will only ever be sent over the HTTPS protocol, making sure that it's encrypted as it's being sent over the internet. We'll see all of this in action very soon. All right, let's see our session in action in Node in the next video. I promise everything is going to start coming together. I'll see you in the next one. Bye for now. Welcome back. In our security example project, we're serving our site over HTTPS. And we've demonstrated that we can log in using Google while following that OAuth 2.0 flow. Here's the catch. Anyone can still go to the secret endpoint directly by browsing to the secret URL and find our secret value. If I go into another browser where I'm not logged in, there's nothing preventing me from asking the server to show me that secret and revealing the deep secrets contained within. Right now, this endpoint isn't very well protected. We need to keep track of whether the user is logged in inside of a session and implement that check so that they can only view the secrets if they're logged in. Where? In this check logged in middleware, which should set this is logged in value depending on whether the session in that request includes a logged in user. And this check will only pass if that session has been properly populated, allowing the request that's been directed to the secret endpoint to hit the request handler here and receive the response. So what are we waiting for? Let's add the ability to handle sessions to our OAuth example here. We start with some built-in passport functionality. Remember the passport.initialize function we called? This is middleware that's part of the passport module, and what the initialize function does when it's called is it sets up the passport session. So how do we populate this session? The one that's been set up for us. This is something that can't be done automatically because our session can look differently depending on what our application needs. And it can be stored in different ways. We might be storing our session in a database that lives in this server. But alternatively, we might be getting that session from a cookie. So as developers, we have to do something to hook up the session as Passport sees it with the session as it's stored. And we decided that for this example, we'd be using the cookie-session npm package, which allows us to do client-side sessions where the entire session lives in this cookie that is populated in the user's browser and sent in every request to our API. Let's get our cookie package set up. First things first, we have to npm install that package. And with that set up, let's go near the top of our file and we'll create this constant for our cookie session module that's coming in through our require statement for the cookie-session package we just installed. We can now use the cookie session module to set up and parse the cookie where our data will live. This is middleware, so we're going to add it right above the passport.initialize call. Because the session needs to be set up before Passport uses it, but we want Helmet to check our headers before we do anything with the session. So what we're going to do is app.use calling cookie session, which is a function that takes our options which determine how our session cookie is configured. So we can choose a name for our cookie by specifying name, and we'll just call it session. We can say, how long will our session last before the user has to log in again? That's going to be our max age parameter here, which is in milliseconds. So for 1 second, we can say 1000, but that's not very long at all for a session. So we can multiply that by 60 for 1 minute and 60 again for 1 hour, which is still fairly short. So let's make it 24 hours or 1 day until the user has to log in again because their session expired. And last, but very much not least, we have this keys parameter. This is the list of secret values that is used to keep your cookies secure. Specifically, by signing your cookie so that only the server can decide what the session contains. The server will sign cookies it sends to the browser with this secret key, and it will, in turn, verify incoming cookies to make sure that they were created with that secret key. This prevents the user from tampering with their user session, modifying it, and saying that they're actually logged in as another user, for example. Each key is a string, something like secret key, but ideally, it should be something that's hard to guess. Preferably something that's randomly generated by something like a password manager. We pass this value in as an array because it's possible we need to change this secret. It may have gotten leaked. Or maybe we've just decided to change it to a more secure value. Whatever the reason, changing this secret value will invalidate all existing sessions. Someone who's logged in from when we were using our original secret key won't be able to use that session to log in if we ever rotate or change our secret key. For example, if we wanted to rotate or change our secret key as a precaution, and we still wanted our existing logins to work for users, we could add a secret key the one that we're rotating in. So maybe it's secret key for rotation. And all new sessions would be signed with the new key. But our middleware would still accept keys signed with the original secret key. Now, at some point in the future, when we're sure that all new login sessions have been signed with the new key, we can remove that original key from our array. And it will no longer be valid when the server checks whether a session should be accepted by the server. Because of this, it's always a good idea to have at least 2 keys being used to sign your cookie session. And as we've already discussed, it's not a good idea to hard code your secret values inside of the source code. Instead, just like with the client ID and client secret, we'll set 2 values. Cookie key 1, which is going to come in from our .env package and will be set on process.env.cookie key 1. And we'll do the same for cookie key 2, which we'll use to validate sessions if we choose to rotate or change the key that we use when signing that session. Just like if we decided to change our signature, the one we use to sign paper documents, like our passport. We would still recognize the old signature, but all new sessions are signed with our new signature. All right, so let's set process.env.cookieKey2, which means that we'll set these values inside of our .env file. We're going to set cookie key 1 to some secure secret key, and we'll set cookie key 2 to some secret key for rotation. Now in our server.js, when we configure our cookie session, we'll use those values, cookie key 1 and cookie key 2. And we can get rid of our hard-coded values. Oh, and we need to make sure that these values are coming from the config object, so config.cookieKey2. All right, our server now understands how the cookie for the session should look. It knows where to look for it and how to parse it, as well as how to manage the life cycle of when that session is valid. And this is really important because we're using a client-side session. We need our cookie to be signed by the server using these secret keys that only our server knows. These are values we should never make public because anyone with these keys could potentially log in as whoever they like and set whatever session values they need to get full access to our server. The security of your user sessions depends on the security of these keys. We're making progress, but we're not quite there yet. Right now, our cookie session that's being parsed by Express isn't hooked up with Passport. And when our user logs in with Google and is redirected to this callback, the session isn't yet being populated by that user's data. Let's do some populating. For that, I'll see you in the next video. Welcome back. We've set up our cookie session middleware. What remains is for us to hook up Passport with exactly that middleware, so that when Google makes a request against our callback here, the session inside of Passport is set and the appropriate cookie is returned back to the browser. This way, the browser will remember that the user has logged in for as long as this cookie session is valid. So back to this passport.initialize function. This is middleware that set up the passport session, which is populated by two functions inside of Passport. Passport has one function to serialize the user data to the session to determine, in our case, what the cookie will store. And Passport has another function to deserialize the user data, or to take it from the cookie and set it to a value that is made available to us by Express. The deserialize function saves the user session from the cookie and places it into this request object inside of all of our middleware and request handlers inside of this request.user property. So serializing means saving our user data to a cookie that's going to be passed around to our user's browser. And deserializing means loading that user data from that cookie into a value that we can read inside of our Express API. All right, that might not seem very clear right now. So let's build out this functionality and keep digging until it makes sense. Those two functions I mentioned, serialize user and deserialize user, we can define those ourselves on this passport object. We say passport.serialize user, and as an argument to this function, we pass in a callback that's executed whenever the user is being saved to the cookie to be sent back to the browser. This callback takes in a user object, that's the user being serialized, as well as this done function, which we call once we've done all of that serialization work. Done is a callback in case we need to do any asynchronous work to serialize the user. For example, making a lookup inside of a database. All right, so let's see this in action and figure out what this function should look like. First, before we dig into serializing, we also have the deserialize function. So passport.deserialize user takes in a similar callback. It takes in an object from our session and returns back the data that will be made available inside of Express on that request.user property. Just like serialize user, this callback also takes a done function, and basically, inside of both functions, we're going to want to call done along with any errors. So if there's no error, we'll pass in null. And the second value is going to be the result. We can start off by passing back the object directly. In this case, whatever is coming in from our cookie is going to be what's populated on our request.user object in Express. In much the same way, we can do the same thing in serialize user. We'll say done, and there's been no errors, so null. And we'll pass back the user and set it as the value of our cookie directly. This is the most basic case, where we're not doing any special parsing or loading of data from a database, but instead just taking the value as it lives inside of our cookie. Just to be clear, we can comment these functions and say that serialize user is when we save the session to the cookie, and deserialize user is when we read the session from the cookie, saving the session to the cookie and loading it from the cookie. We'll see what other types of things we might do in these two functions in just a second. For now, let's finish hooking up all of the pieces of our session with Passport and our Google OAuth flow inside of our two endpoints here. To save the session when the user logs in and serialize it in a cookie, we need to set this session parameter when Google hits our callback URL here to true. Or we can remove this parameter entirely because it's set to true by default. And the final step is to add our Passport session middleware right below where we initialize Passport in the first place. This is so that Passport understands our cookie session and the request.user object that's set by the cookie session middleware. We can call app.use on passport.session. What this does is it authenticates the session that's being sent to our server. It uses these keys and validates that everything is signed as it should be. And it then sets the value of the user property on our request object to contain the user's identity. That is, the passport.session middleware will allow the deserialize user function to be called, which in turn sets request.user, which we can use in any of our Express middleware. And that's it. This passport.session piece was the last thing we needed to have a session that keeps track of our logged in user. Now, what does our session look like in the browser? Only one way to find out. npm start. Here we go. I'm going to open the network tab of my developer tools. And because I'm already logged in with my Google account in another window where I'm using one of Google's other services, when I click Google Login, I won't need to pass in my Google password. We're going to see the entire OAuth flow complete with a single button click. We hit the auth/Google endpoint inside of our server, which kicked off the entire flow and redirected us to Google's OAuth endpoint, where we are using the authorization code flow and pointing Google to redirect us back to our callback here once it's complete, which is what happened. Google knew that we were logged in, and we got our authorization code back in our callback, at which point Passport knew how to handle this authorization code and exchanged it for an access token, as well as our basic Google profile information. And we were redirected to our homepage. But here's the great thing. We're now using a session. So somewhere here in our callback, when we get that successful login, we should be setting the session inside of our cookie. Check it out. Our cookie session middleware has set this session value. That's the value that we assigned when we configured our cookie session middleware. And the value of this cookie is this signed string here, which contains all of our session data. In our case, it contains our Google profile information that came back in our verify callback. When the entire OAuth flow has complete, we get this access token, as well as our profile information, and optionally that refresh token. And we're logging the profile information that Google sends back. That's what we see in our console, in our terminal right here. Check it out. I've logged in with an account with this email and this ID. This object that's being logged is what is in turn being serialized and deserialized from our cookie. That's what we're seeing in our browser in this set cookie header. We can also see that it's being set on the root path and that it expires 24 hours from when we logged in. The secure flag is being set to make sure that this cookie is only ever sent over HTTPS, and HTTP only is set so that we can't access this cookie from JavaScript. If I do document.cookie in the JavaScript console, you can see nothing is being returned because we're trying to access the cookie data using this JavaScript property. But if we go in our application tab here under cookies, we can see that localhost is setting 2 cookies. One with the signature of our session and the other with the actual session data. Our user's login will now be remembered for as long as the session is valid and that cookie hasn't expired. Everything is coming together. Good stuff. In the next video, let's spend just a minute to really solidify our understanding of how to serialize and deserialize our session information. I'll see you in the next video. Welcome back. When we log in with Google as our social sign-on provider, we're now setting this session in our Node Express API. That's this value right here. But what we're doing is we're just taking the profile as it comes in from Google and setting that as the session in our cookie and reading that entire profile back whenever that cookie is sent to our API from a browser. As we've seen, the Google profile data is actually fairly large. It contains a lot of this metadata, which duplicates our email, for example, in a few different spots. And if we look back in the browser, we can see that this session value is fairly long. It's taking up, in my case, 771 bytes. Not quite the 4 kilobytes that my browser limits cookies to, but it's also not that far off. We can limit the data that we're saving in our session by taking advantage of these serialize and deserialize functions. Let's take a look. The serialize user is going to take the Google profile, the one that we get in our verify callback, and it's going to create that first cookie for our session. Right now, we're taking the entire user profile, but instead, we could pick and choose certain properties, or even just select one property like user.id. That's this value near the top, this ID value for our Google profile. We're going to use just this ID in our session to minimize the size of data that we're sending back and forth, and because for the purposes of our example, we don't need any specific data about the user. We're just happy with the fact that they've logged in successfully. If they have a valid Google account, we're going to say, all right, you have permission to get that secret value from our API. But if we were using server-side sessions, for example, we could store just this ID in the cookie, and if we needed to know more about the user to determine what they have access to, for example, what permissions they have in our API, well, this deserialize user function would be called when we take that cookie and read it when we're handling a request. The cookie data would be passed in as this object. The cookie would be verified with our secret key, and we would take this object with our cookie data, and we could look up the user with that session by their user ID inside of our database. And our database might store this user's permissions, their email, and any other data we need. So this deserialize user function might do some database lookups, like a user.findById. And in this case, the object that we're being sent in our session is an ID. It's this user ID that we serialized. So we could find by ID, and once that fetches our user data, we could say .then whatever data we fetched about our user can be sent in the done callback, just like before. And we would comment this other done statement out. So now, even though our cookie only contains the user ID, our request.user object is going to contain all of the data in our database about this user. This is just one example. Passport provides the functionality to implement our session pretty much however we like. But in general, doesn't hurt to start simple and stay simple as long as you can. So we're not going to look anything up inside of a database. We're just going to pass back the ID that we read in from the cookie. And now, if we rerun this server and go back to our browser, let's clear our cookies and log in again. Looks like the session is being set correctly. We have our signature, and our actual session is now much more efficient. It's taking up only 67 bytes, which is nowhere near any of our browser's limits. Very nice. All right, in the next video, let's take advantage of all of this session logic that we've implemented and complete our check logged in middleware so that only logged in users have access to endpoints that use this middleware, just like the secret endpoint. All right, this one wasn't too bad, and the next one's going to be fun, so I'll see you there. Bye for now. Welcome back. What was it all for? Why did we go through the entire OAuth flow to log in? Why did we set up our cookie session and the Passport middleware? We did all this so that we could protect some of the data in our API with this middleware that restricts access, in this case, to our secrets to only logged in users. Right now, our check logged in middleware is passing through regardless of whether the user is logged in or not. We've just hard-coded this value. Let's fix that. We want to secure our secrets and make sure that users who aren't logged in only get this 401 response that tells them that they must log in. Our Passport session middleware is setting this request.user property inside of our express request object. We can log it right here in our middleware. We'll say console.log current user is request.user. This should log that the user is this deserialized user that's been read in from the cookie. And remember, the cookie is being populated with just the user ID from our Google profile. Again, the one that comes in our verify callback when we complete the OAuth flow. So what this means is that to check whether a user is logged in, we can set the isLoggedIn flag to request.user, and if this is a value that's been populated, if it's not null or undefined, Passport has validated the session. Remember, that's what the Passport session middleware does. It's deserialized that session and given us the user ID, and this request.user value is available to us. Are we right? Does this work? We can test things by starting up our server. In our browser, because we've probably already logged in and we have a cookie being set with our user session, to log out, right now we'll clear our cookies and see if we can access our secret endpoint. We may have to remind the browser that we accept the self-signed certificate. And there we go. We're getting our JSON error telling us that we must log in to see our secret. In our network tab, we can see that the secret endpoint is returning back 401 unauthorized. All right, so what happens if we go back in our browser and this time log in with Google? We need to keep in mind what we need to realize. There's a little bit of a surprise here. When we cleared our cookies, we effectively removed the session that stored our login inside of our Node application here. So we signed out in a very manual way from our Node application. But Google is still signed in. My Google account, unless I log out of it in one of Google's own services, I'll still be able to sign in to our application here without putting in my password, just by clicking this Google sign-in link. And that's exactly what happened. Check it out. Our session was populated with my Google user ID. That's the value that's stored in this cookie string. And in the network tab, we can see that the OAuth flow was completed. There's the auth request, and there's our callback URL. Now, with our user session living inside of this cookie, we should be able to access our secret value. Let's see if our server is protecting our data and allowing access when it should. Awesome stuff. As a logged-in user, we were able to access our secret no problem. Back in our server, we can see that the user that's populated in our express request object is being logged as well. What we see here is the user ID that we saved into the cookie, which came from the Google profile. for the user that just logged in. Now, because our middleware here that protects certain data in our API, because this is security related, we can be extra cautious here and rely not just on some user property being populated on the request, because the user could be populated by all kinds of different middleware. So we can be more explicit and use the request.isAuthenticated function that's built into Passport and checks specifically that Passport found the user in the session. So we'll set isLoggedIn to request.isAuthenticated and that this user property lives in our request. We could use just one of these conditions, but using both gives us some extra confidence, which means we can remove our to-do. We've done what we need to do. And we're making use of this data that Passport is exposing for us to restrict who is authorized to access our API. Things are looking good. Just one more thing. Back in our application, what would happen if in our other window we logged out of our Google account? Would we need to sign in to our application from the very beginning? Let's see. Back in our application, I can refresh this secret endpoint and notice that the session is still there and I still have access. This makes sense because our session from our previous login is valid from 24 hours after we log in. All right, let's figure out how to implement our logout functionality in the next video. I'll see you then. Welcome back. How do we implement sign out functionality into our Express applications? We've seen that clearing the session cookie in our browser's development tools effectively does log our user out. But what if we wanted to allow the user to log out by just clicking some button or a link like sign out? Let's find out. Because we're clicking on a link, our request is going to be a GET, just like we've defined on this logout route. So what do we do with our request and response when the user asks us to sign out of the application? Well, Passport exposes a logout function on the request object. This can be called on any route by just calling request.logout. Exactly like what we did when we cleared the session cookie manually, the logout function here will clear any logged in user session and it will remove that request.user property from this request. So what this does is it removes request.user and terminates or clears any logged in session. So that will log our user out. But in general, if a user is on some protected route and they click log out, we want to navigate that user away from that protected route so that they can browse the site anonymously or log in as another user. One common approach is to redirect our user back to some home page, which we can do by returning from our request handler here and just saying response.redirect, pointing the user back to that root route. We've already done all of the hard work with our user logged in, our session taken care of, and the OAuth flow implemented, we can now take full advantage of the convenient features of Passport that cover common use cases like logging out and checking whether current users are authenticated or not. Let's test our logout function. We'll make sure to restart our server, npm start, and now in the browser, I'm already logged in, the session is populated, and I can view the secret endpoint. But let's see what happens when I sign out. All right, so I still have a session. Let's see what happened in the Network tab. The latest logout request here at the bottom was a GET to our auth logout endpoint, and that successfully redirected us with this 302, this redirect response, to the home page of our application. But something is going to give us a lot of insight into what's going on. What is that? It's the headers of this response in this redirect request. I'll scroll down, and we can see that part of the headers was this set cookie for both the session and the session signature. In our Application tab, these values for the signature and session are different than what they were for a logged-in user. Notice that the session value here is much shorter than it was when it contained our user ID. It's only 27 bytes. That's fine, it might be shorter, but what exactly does this value contain? What is our session? Well, this random string that you see here, regardless of whether our user is logged in or logged out, contains an encoded session that's set by Passport. By default, this value is base 64 encoded. And remember, it's not encrypted, it's just signed to prevent tampering. But we could take this session value here, copy it, and if I do a search in Google for base 64 decode, I can take one of these handy base 64 decoders, paste the value, and let me make this a little bit bigger, and we'll see that anyone with access to our cookie can read the contents of what's in our session. Let's see. I'll click this decode button, and our session is currently just storing this empty Passport object. So our user is currently logged out, even though their session here is populated. There's no user being contained in this session. And so if I try to view the secret endpoint, our check in our source code here, where we check that the current user is authenticated and this request user object is populated, well, we can see that for our latest request, the request.user value is undefined. So it looks like our check logged in middleware is doing its job just like it should. And our log out functionality is successfully clearing our users' sessions. Very nice. In the next video, we're going to do a fun little experiment. I'm looking forward to it, so I'll see you then. Let's do a little experiment. Before we go, I want to answer a question you might be having given what we've learned in the past few videos. Here's the situation. We've just signed out. What happens if we log in and populate our browser session again? Let's see that in action. All right, it looks like my login to Google has expired, so I need to sign in again, go through that handy OAuth flow, log in, and get my user profile from Google, which will in turn populate that session. Google has redirected us to our home page, and in our cookies, our session value is now another base64 encoded string, or whatever encoding the cookie session module is currently configured to use. It can change, but right now it's base64. So this value can be decoded just like our empty session. I can take this value, and in our base64 decoder, let's see exactly what it contains. Decode, and if we scroll down, we have our passport session. Right now, it contains the user ID for the account that's signed in to our Node application. But check it out. Let's do a little experiment and copy this session value, scroll up here, and encode a new base64 string with this session, and I'll make this bigger again. But this time, I'll change the user to another ID, one that doesn't belong to my Google account. Maybe it'll be user ID 33333. What happens if I encode this session value and try to claim to my server that I am user 33333? Well, we can test this out by encoding this value. Let's do that down here. And taking the encoded base64 string, which we'll put inside of our cookie. I'm going to edit this value and paste that base64 string into the session, which we can see now contains this new value, this new base64 string with our fake session. And now my browser is going to try to claim to Passport.js and our secure node server that I am a user who I'm just pretending to be. I'm not actually user 33333. Let's see what happens if we try to access the secret endpoint while making a fraudulent request with a tampered session, one that we've modified, that doesn't match the signature. Let's see. Show me that secret. Very nice. All right. Our server isn't quite happy with that request, and it's telling us that we need to actually log in as a valid user. In our server logs, we can see that for that latest request, the current user was understood to be undefined, or in other words, things just didn't work. What happened is the Passport session middleware didn't find a user session because our session cookie from the cookie session middleware wasn't successfully validated. The signature didn't match the actual value of that session cookie. And so Passport told us that a valid user wasn't successfully authenticated. Things are working as they should. That's great news. All right, that's all for now. I'll see you in the next one. Bye-bye. Welcome back. We've done it. We've done so much in this section. We implemented social sign-on with Google. following the OAuth 2.0 authorization code flow. We went over tokens and cookies and saved our login in a user session. And in the meantime, we've talked about many important security-related topics, like digital certificates, securing our cookies, and even a little about cross-site scripting. Now, there's a lot more we could cover. Some possible next steps might be implementing refresh tokens, that value that we saw in our verify function next to the access token when we completed our OAuth flow. We could use one of these long-lived refresh tokens so that our users don't have to log in all over again when their access token expires. Instead, we can use these refresh tokens to get a new access token, which might include some slightly different permissions for the user. If, for example, what that user is allowed to do has changed on the server. These refresh tokens aren't always required, but they do provide some nice benefits. Or we could talk about managing our sessions using various different databases, like MongoDB or Redis. We would use these databases if we wanted to do server-side sessions as opposed to client-side sessions. And we could add more levels of security by, for example, giving different users different kinds of permissions with different levels of responsibility. This would take advantage of what's known as role-based access control, where each user has a role that allows them to do some specific set of tasks in our API. And we could store these roles inside of our user session. Security is a vast topic, and there's really so many things that we could explore. My hope is that this section has given you a practical foundation of how security and authentication work in real-life Node applications, and especially in those large-scale applications that we use on a daily basis. Those Google services, or blogging platforms like Medium, and source code repositories like GitHub. We learned the slightly more complex OAuth flow because I believe that this will give you a head start if you're ever working as a software developer on one of these large web applications, or if you're ever asked to add social sign-on to some application, or even if you're just wondering how these authentication systems really work under the hood and why you're being redirected to different domains as you log in. In this course, my goal has been to really balance things so we're not learning just frameworks, but also concepts. We want to balance learning practical things that we can apply on our own projects or at a job with these general concepts that help us to understand what's actually happening under the hood. When you've been working as a software developer for a couple of years, you realize that frameworks change quickly, but concepts and our understanding of them can stick with you between different packages, different frameworks, and even apply to different programming languages. So, with the exception of some frameworks like Express, which are rock solid and provide a good foundation for other frameworks, I try to focus more on first principles, those concepts that everything else is built from. with authentication and login, things are always changing. We're constantly making things more secure. But some of these approaches have stayed more or less the same. Standards have been created, like OAuth, and patterns like social sign-on. Learning these things that will apply for years to come is a more efficient way of spending our time, especially when there's so many things to learn. All right, well done, pat yourself on the back, and I'll see you in the next one. Bye-bye.